One, just because I really wanted to see where that chaos class.
Okay, hi everyone. We're live for day 2 here at the IEEE CIS summer school having to do with game development. Nice to meet you all. I'm Dr. Joseph Alexander Brown. I'm a professor here at Thompson Rivers University. Just a bit of a heads up to those of you that are in the room under basically BC privacy law and etc. We are recording inside of this room. You can see the camera here. If you don't want to be in the recording, please do not be on the recording. If you don't want to have your voice or names broadcasted, please don't announce that inside of that room. So this is your fair warning at the start. If you don't want to be on the stream, you do not have to be. Secondly, we are here at beautiful Thompson Rivers University on the unceded territorial lands of the Secwepemc to Kamloops peoples, and we service other peoples inside of British Columbia. We have a beautiful day here today inside of the Secwepemc regions. Even this morning, I've just woken up and got to see the beautiful mountains and the new house that I just got within the area here, and I'm really thankful to be on these lands. The great thing about these lands, too, is we get to invite in some wonderful visitors, and we have 2 coming in here from the University of Southern Denmark today, and they've been able to see the beautiful lands inside of Kamloops and see Canada. And I'll let Marco give his kind of CV piece of this.
Yeah, that's perfect.
But Marco, we've known each other now for...
I don't know, like...
2014, I think is 2014,
so.
2015, somewhere around there. And I had the wonderful opportunity to go and visit him inside of Copenhagen. And so I'm so glad that you're able to join us here and get to experience it from the other side. And I was thinking something kind of interesting the other day, because you just had your first wedding anniversary.
Yeah, that's true.
You had your first wedding anniversary just recently, and when I went over to Denmark, I had my first wedding anniversary without Beth in Denmark.
Oh, it's a shame without Beth, though.
Yeah, I know, but I'm saying I had my first wedding anniversary in Copenhagen, and here you are, and so it's a weird symmetry.
It's destiny. Let's call it that.
So with that, I will hand over to Dr. Marco Soria of the University of Southern Denmark to talk about fundamentals of AI and Unity. Thank you.
Thank you very much, Joey. All right, hi everybody. Nice to meet you. So, as Joey has mentioned, my name is Marco. Just to tell you a little bit more about myself. As Joey mentioned, I'm an associate professor at the University of Southern Denmark. Before that, I did a PhD in effective music generation for games. So my interest in games is a huge one, I would say. It's really the main field of my research, together with artificial intelligence, music, and a lot of other things around that sphere. Before that, I studied game design. I have a master in that from the IT University of Copenhagen. And I do like to make a lot of weird stuff. I really enjoy making systems that generate some kind of content, that create things. So that's really something that I really liked. Before I moved to Denmark, I'm originally from Italy. I used to play music a lot. I studied at an academy, and but I also was studying computer science. And really, I managed, thankfully, with a lot of luck as well, to put all these passions together during my PhD and really put together music, games, artificial intelligence, and all this kind of stuff. So I'm hoping we're going to have a lot of fun, and I'm going to show you also tomorrow some fun things related to music. If you want to see a bit more about my stuff, or about what I do, you can look up my website. It has a list of publications, small games that I made while I was a student and a researcher in general. And yeah, so if you have any questions about that, of course, you can catch me at any point during the day. But I also, since we're here talking about games, I also want to tell you a little bit about my favorite games, because it seems only fair. As you can see also from my shirt, I'm a huge Legend of Zelda fan. I love those games. I just finished playing Tears of the Kingdom, obviously. Amazing game, beautiful. But I also like, in general, narrative games. I don't know if you know Night in the Woods. It's a great kind of adventure game, narrative game, and I think it really resonates with our generation. And I hope you don't mind that I put myself in our generation. Of course, I'm a little bit older, but I think we have a lot in common still. I don't know if you know the Longest Journey series. That's also really good. It's I think 3 games that it took, I think, about 20 years or something for all of them to come out. So it's a bit weird in that sense, but super nice. Hat in Time is from where this GIF is from. And any Zachtronic games, Witcher 3 or RPG games, all that kind of stuff. Since I know that there's a lot of software engineering, computer science this year in the room, if you haven't played any of these games by Zachtronics, I really suggest you try to do those. They are usually programming-inspired games, super nerdy, but you actually get to learn a lot of interesting stuff from those. Right, I think that's it for my introduction from games. Of course, we're welcome to talk about games a lot more later, but I think we can move on to today's menu. So today we're going to talk about AI techniques in Unity. And since we don't have a lot of time, it's only today that we have, I'm not going to go too deep into algorithms. I just want to focus more on some practical aspects. So we're going to see a couple of techniques that are very common in the gaming industry for doing navigation, for doing agent behavior, and we're going to see some practical exercise, and we're going to try to figure out how we can do that in Unity. So sadly, we're not going to do more cutting-edge stuff. For those of you that study here, I'm sure you'll see a lot of more interesting cutting-edge stuff with Joey during your courses. But sadly, today we're just going to focus more of industry-level stuff. So mostly we're going to look at navigation and decision-making. Right, so let's start that with pathfinding. I think that you probably know the term. Anybody knows what pathfinding means? What's the problem? Yes? Exactly, finding a way to move from one spot to another. It sounds simple, right? But in games we have this problem all the time, and we've also seen, I'm sure you have a lot of examples in your memory of pathfinding gone wrong, where we have agents or NPCs that kind of like get stuck and start walking straight into a wall, stuff like that. So it is quite an interesting problem. So I just want to talk a little bit about what is the standard here, what is actually happening usually in the industry when we want to solve these problems, and we're going to see how to do that in Unity at the moment. So I think you already kind of mentioned what navigation is. The idea is that we want to move our agent, or I don't know if you have heard the term agent before, but usually in artificial intelligence, that's what we call something that has agency, that wants to make decisions or do something within the environment. So I might say agent, but if you look at it in the terms of computer games, usually it could be an NPC, something like that. that wants to move around some environment where there are some occlusions, some walls, for example, or stuff that we cannot pass through. Right, and that leads us to our first algorithm of the day, A star. I don't know, how many in the room have heard about this? 3, 4 people. Okay, so not a lot. Again, we're not going to go too much in detail about exactly how these algorithms work, so don't worry about that. We're going to make it more accessible, but I want to give you an idea of the general concept here, and then you can look it up yourself and go deeper if you're interested in that. So A star is what's called the best first search algorithm, meaning that we're trying to find a solution to a problem, right? The problem, of course, here is to move from one point to the other, which is the best path that we can take. And by best first, we mean that this is an algorithm that tries to always use the best guess that it has to build up on its successive guesses. It finds the shortest path between 2 points on a map. It does that consistently. So that's why it's actually kind of the industry standard. You know, in any game, wherever you see something make a movement, you can be pretty sure with like 99% certainty that behind that there is A star working. Because it's also very performant. It works really fast. And the result is, and the result is guaranteed. With just this small kind of like caveat, which it needs an admissible heuristic. Have you ever heard the word heuristic? One person, two, three? Okay, just so that we're on the same page, it sounds like a big mouthful. It's a big word, but it actually just means it's a guess. So this is a type of algorithm that doesn't just do things based on the information that it has, but it also makes some guesses. So this heuristic is the strategy that it has to make guesses about how far we are from the goal. So if that's a good one, if it doesn't overestimate how far we are from the goal, we always get the best possible path. Otherwise, there's some issues there, but most of the time this works very well. To give you a more graphical example, this is kind of how A star works. So we have a starting point down here, we have a goal up there, and you can see that A star kind of starts by expanding the search space. Once the GIF loops, you'll see that it starts by going in a straight line towards the goal. And once it finds that it can't go further, it starts kind of expanding and looking around until it finds a way that we can go through the obstacle, and then again it moves in a much straighter line. So this is what the best first part is. When it finds here that, okay, this looks like it's the best path, it goes through there. There is no, insurance that there won't be another obstacle over here that stops it. But if it does, then it will explore some other different paths. Nice. Any questions? Does it kind of make sense as a visualization? Perfect. Very good. I hope I'm not going too fast. Let me know if you need a small break or if you need me to slow down. Also, feel free, I forgot to mention that, but feel free to interrupt me if you have questions. I don't mind at all. So at any point, just let me know. Right, so if you remember this, it looks like we are breaking the space in different points, right? That are connected. Do you know the name of a structure where we have these kind of nodes that are connected with each other? Graph. Very good. Exactly. So I hope that this is not too new to everybody, but a graph is basically a structure where we have nodes, these points over here, connected with some kind of edges, some kind of connections between them. So one of the things that is important about A star is that it works on a graph. So if we want to apply that to a virtual environment, our Unity game, we do need to somehow put a graph on top of it, on top of the environment, where usually key places can be represented as nodes, and the connections will be the edges, the connections between the nodes. So there's a lot of ways that you can do this. One of the ways could be this. We just take a grid, and we put it on top of our environment. And if we have some walls there, we just take away the nodes. They're not viable, not places where we can move. and then we just connect these. So this could be a graph of this map where we have connection between close by nodes. Everything makes sense up until now? All right, very good. This is just for, I'm just gonna leave it in the slides. You can take a look at it later. It's the pseudocode for A*. I usually like to give the pseudocode because it's nice to have a more high-level description that you can try to implement yourself. I would actually recommend you try to do that. In Unity, it's already implemented. You don't actually have to do anything of this, but it's a good exercise. Try to take this and make your own implementation from the high-level description. Right, so I have a question for you. I told you A* is great, right? Because we can always find the best path from one point to another. It always works, it's perfect. So why are we still talking about pathfinding? Yes? It's actually really performant. So compared with other algorithms that do the same thing, A* is really fast. It's really good. Yes? That's a good point. A* is very efficient. So A* always finds the best path. If we want something that might be more realistic, we don't always take the best path, right? When we do things, we might go a bit around, have some randomness. So you're right that if we want to make something that is not the best at doing things, but it's the most realistic, we might want to tweak it a little bit or put some randomness in that. Yes, that's a very good point, actually. It's quite interesting. Thank you. Any other ideas? Let's think about something. I'm sure you're all familiar with a Roomba, right? You know, the small vacuum cleaner and so on. If you put a Roomba in this room, do you think it will be able to navigate it correctly if we assume it has A* on top of that? Possibly, but you know, imagine we just take our Roomba, we put it down here on the ground, and somehow we can tell it, you know, go down there in that corner. Would it be able to? Yeah? Exactly, like we need to know the layout of the room somehow. I don't know if any of you has one, but at some point I got one, and it was really funny to see it go around and crash and everything. It was very entertaining, but it wasn't very efficient, obviously. So one of the main problems with A* is that we do need to have this graph. We need to know beforehand what is the layout of where we are. Usually in games, that's pretty chill, right? That's pretty easy because, you know, it's inside a game. We can just see everything in there. But if we think about the real world, then it becomes more complex. If I imagine a robot like the Roomba in an unknown environment, it would not be able to use A*. In theory, it can, sure, but if it doesn't know how everything looks, it won't be able to do anything. So that's kind of one of the reasons why pathfinding is still a problem to this day. And we're gonna see a bit later what does that means within games and what kind of solutions we found to get around this. Before we move on, though, I want to show you something else. So A*, as we said, you know, pathfinding algorithm, very nice. You can go from one spot to the other. But it's not limited to that. Like, you can use this for a lot of other things, because the general concept, if you look at it very abstractly, is that it just finds the path between something and something else inside a graph. A graph can represent a space, but a graph can represent a lot of other stuff. So you can use it for a lot of interesting things. I'm going to show you this. This is from an old competition, an old AI competition that sadly doesn't exist anymore, for making bots that play Mario. So this Mario is using A star to move around, and yeah, with the goal of going to the right side of the screen, right? It's pretty good, right? It doesn't look very human if you think about it. You know, like we don't play like this unless you're maybe, you know, like the top 1%. Like if you're insanely good at Mario, but most people wouldn't play like this. You can also see that it ignores a lot of stuff like coins. It doesn't care. It only has one goal in its mind: going right to the right edge of the screen. Right, and I wanted to show you another one. It's the same bot, but instead of moving to the right-hand part of the screen, now it follows the mouse. So you can see it's a little bit more controllable. So have you noticed that it's moving, right? But it's not only moving, it's also shooting and doing other actions, which sounds like something a little bit different than what we were talking about A-star before, which was purely movement from one spot to the other. Oh yeah, now it's being a bit mean. But still able to figure it out. Right, so I think that let's take a moment, and I would like you to, you know, let's take 5 minutes, and you can chat with each other and see what do you think is happening here. How do you think, you know, A-star is being applied to this problem? And I think we can just take a little bit of time, have a chat with each other, and then we can see what you think in a couple of minutes. And I'll get some coffee. So, what do you think? You have any ideas?
Making a decision basically on every frame.
Yes.
Self-preservation is the first course of action?
Mm,
Because it seems to like do a little weird little frame generator when it gets really close to the sliding shelf.
remember one thing. So since it's A-star, it needs a graph.
Yeah.
So what is the graph? That's the real question.
I guess they're pixels, the X and Y pixels.
The X and Y, yeah. Okay, so imagine that we want to build a graph on top of this, right? What could we do? We could make a grid, right? And we just kind of like make the entire map into a grid of places where Mario can go and Mario cannot go. But then how do we decide if a place in the grid is safe or not? Yeah, so if there is an enemy, maybe that's a place we can't go. We take that away. It's kind of like a wall, right? So if we do that already, we have our Mario agent that will navigate the level, avoiding enemies, because they are not on the graph. They're outside of that. Right, but then how do we decide to go from, let's say, you know, if we imagine we have a node over here around Mario, and we have a node over here, how do we move from one place to the other? What kind of actions should we take? Because again, this is not just something where it can just move, right? We have to make actions to move Mario, if we're thinking about, you know, our gamepad and so on. Yes? What, sorry? We can jump over that, but then it means that we would have to know that the path is that if we go from here to somewhere over there, and then there again, right? Perfect. I think I'd like to show this one. I'll try to remember to send you the paper as well at the end, because I think it was really smart the way that they decided how to build the graph. So the graph is built around Mario. The goal, again, right border of the screen. Those parts are easy. But then they build the graph based on what you actually can do as actions, right? So if I press the right button, I know that at the next frame I'll be here. If I press right and speed button, I know that I will end up over here. So we can build this graph around Mario based on the current speed of Mario, what kind of buttons we can use. And that means that we can find our path. And the only thing we need to do is that we need to take the action that's the best one at the level of Mario. And then next frame we can recalculate things. So if enemies have moved, some paths will be open, some paths will be closed, and again we keep doing that. So I think that's a really cool, you know, like really smart way that they got around this to build the graph around Mario. And if you think about it, this is also a pretty tiny graph. Of course, I think they made it a bit larger so they can see a bit more into the future to avoid, you know, having too short-sightedness. And we just take what looks like a good action now, but then it's going to bite us in the ass in the future. But in any case, we don't have to have the whole level gridded out. We just need to know what's around Mario right now, which is actually how we play it, because we don't see all the level, we only see the screen, right? A little bit around Mario. Yeah, and as I mentioned before, as we were talking about it, if there is an enemy that just becomes an inaccessible node, it's out of the calculation. We don't even have to look at it. So the only let's say, complicated thing here to do is that we need to build the graph at every frame, but it's not a big graph, so it doesn't take that much. And A-star on small graphs works super fast, so we have no issues with that. Right. Before we move on, I said that this was something that was part of a competition on Mario level playing. Sadly, that competition doesn't exist anymore. Just so you know a little bit of fun history there, it's because Nintendo came down on it, like a brick, like a ton of bricks.
Shocking loss.
Yeah, shocking, absolutely shocking. It was completely, you know, an academic thing. You know, there was a lot of people in our field that were submitting things to this. It was an implementation made in Java of Mario. We had a lot of different tracks because it wasn't just playing; it was also level generating and so on. And then Nintendo just hit everybody like with this cease and desist because no, we cannot have that. Even like, yeah, you can't do that apparently. Very annoying. But there's still a lot of interesting competitions on AI and games if you're interested. So yeah, hit me up at some point later in the day if you want to know a couple of cool ones, if you would like to participate in some of them. But sadly, the Mario one doesn't exist anymore. That's gone. Right, then I think that leads to our next topic, NavMesh. I think you might have heard the name before, especially those of you that have used Unity a little bit more, because there is a component, like a chunk of Unity that's called that. And I want to unpack a little bit, what does that mean, and also what does it mean in Unity? How do we use that? So if you have ever encountered it in Unity, it looks something like this. It looks kind of like an overlay that you can see on top of your level. What it does is that's basically the walkable area, the area that can be navigated by your agents. By the way, NavMesh stands for navigation mesh. Quite obvious, honestly, but it's good to say just to make sure. And you can see it as kind of an abstract data structure, which we can use to aid our agents in figuring out how to move around the level. But what is the problem here? Why do we need this algorithm? Again, we're not going to see in detail how the algorithm works. You can look that up yourself if you want to. But we're just going to see at a higher level what is the problem we're trying to solve and what we actually get out of applying this algorithm. So A-star needs a graph to work, right? How do we build a graph? We said before we can do that thing, right? But we can also do this. If you look at a NavMesh a bit closer, yeah, sadly I think the quality of this image is a bit low. But if you had one in, actually let me just find, I think if we just search NavMesh here and we find an image, we should be able to find something that looks a bit more obvious. I just want the image, thank you. Oh, I don't use Google that much. Okay, there we go. So this is a NavMesh in Unity. You can kind of see that there are these polygons here. The space is broken down in these different polygons. So that's how it looks, and I tried to represent it here in our slides like this. So as we said, we need a graph, right? So how is this thing a graph? Well, we need nodes and we need edges, right? Nodes are these ones. So each polygon becomes one of our nodes inside our graph. What about edges? How do you think these nodes are connected to each other? What, sorry? Well, like, for example, this one. With which nodes is it connected? So this one and that one, right? So if we have a side that's shared, then we have a connection. So there we go. There's our graph. Simple, right? Of course, the way that you have to build up the algorithm to figure out where do these polygons go, it's a bit more complex, but again, we're not going that far. But that's the general concept. What we're doing in a NavMesh, when we're building it, is we're just building a graph like that. So why do you think it's nice to use a NavMesh instead of the method that we saw before with the grid? Yes? It's more scalable, but why is it more scalable if we look at this? You're right, but why? Exactly, like we need to have a lot more dense nodes, right, in this scenario. And if we imagine that the map becomes bigger, we need to have more nodes and more nodes. But even just with this, if you look at this, I haven't counted them, right? But you can see that there's a lot of nodes over here. Here we have, I don't know, maybe 15-ish. It's quite small, graph-wise. So if I want to go from here to somewhere down there, here I would have to go through a lot of different nodes and different options before finding the right path. In this case, if I want to go from here to there, it's pretty bloody obvious, right? there's not a lot of things that we can do. There's not a lot of nodes that we have to go around. So basically, NavMesh creates an optimized graph that we can move around on using A-star super quickly. So even if we have a huge map with a lot of complexity, a lot of different weird places, we can get something that we can use very easily, can run on the limited resources that we usually have when we're talking about computer games, or it's to some degree. But like we don't want to use too much power. Yes? Yeah. Yeah. Yeah, absolutely. Also, if we look at this, for example, area over here, we have a lot of nodes, right? But here, since there's no obstruction, it's all like a very easy corridor. We just have one block, which is super easy, right? So you usually see the complexity of the nav mesh appearing more when there is some corners, stuff like that. Right. Does that make sense? Do you have any questions? No? Perfect. One question. Yeah, of course. Oh, sorry. I'm sorry, I couldn't hear you super well. Yeah. Okay, sorry, I'm just going to go back in front. I think that there is one of the things to keep in mind is that this is not a substitute for a star. It's just the step before, right? We need to build the graph, and then we can use a star on top of that. About your questions about kind of hugging the corners, as we can see in, if we look at it on the actual Unity thing, usually it doesn't get all the way to the edges. We have some kind of space so that we're sure that our agents are not actually bumping, like going straight into the wall, but there is a little bit of an edge. So we can avoid that kind of weird stuff happening.
So for each of these big polygons here,
yeah. It's
going center mass to center mass to center.
It does not. It does not. I'll show you in a moment how it moves, or at least more or less how it moves between them. But no, it doesn't go to center mass. Otherwise, that would look weird, right? Yeah. It would just not look very natural. So the node position doesn't really matter that much because, again, imagine that you have this abstract version of this where A star works because A star is just, doesn't need to know about any of this actual details. Just needs to know this is the graph, this is where this is the polygon I want to start from, this is the polygon I want to go to, and that's it. Doesn't need anything else. And then instead, when we have the movement actually happening in Unity, we can, Unity does some tricks to kind of make it more smooth, interpolating a little bit, so it moves correctly or in a way that's more natural. But I'll show you that in a moment. But mainly, just to summarize again, the main thing here is that this is something we do before A star. It creates our graph, and it creates a much more optimized graph than just throwing nodes on a grid. So there is a small catch in this, and I have another question for you. Do you think any polygon could be part of a nav mesh? So if we go back to the example here, if you look at that, can you see any, let's say, common properties of those polygons? Can it be any shape, any form, or is there something that you think it won't be allowed? Maybe I'll give you a couple of minutes again to talk with each other, and then we can get to it, so you have a bit of time to chat. Any guesses? Are all polygons fair game or not? This one has 5 sides.
Okay, so the line across the wall would be its own side too?
Yeah, like this, like this would be. Well, okay, maybe this is one side. You're right. Okay, but it can have more. It can have as many sides as you want. So that's not a problem. Not really. Yes. Yeah. Yeah, that's a good point. We'll see later that you can actually have those, but they are kind of separate levels. For example, there are different parts of the nav mesh that are not connected, so you can't really move between them, even if they exist. It's a place where you could walk, another place that you could walk, but there is just no way that you can move from one to the other. Let me give you a hint. If you look at these two, can you see any difference between them? Yeah. Right, and what do you think that could mean if in terms of navigation? So let's imagine I want to go from here to there inside the polygon. What could I do? Straight line, right? That's nice. Can I do that for any combination of points here? Right? What about here? No, right? Because if I want to go from here to there, then I'm going to go outside the polygon. Or in the terms of our game, I'm probably going to run into a wall or something. So that's the one characteristic of the polygons in a nav mesh. They have to all be convex. Otherwise, we don't know how to move between them. Because as we mentioned before, right, this is something we want to use a star on, but a star just tells us you go from this polygon to this polygon to that polygon, not exactly how we move in the real space. So to know how to move inside a polygon, we're just keeping it as easy as we possibly can. So we just go in straight lines, right? What's easier than that? But we need to be able to do that. And that's why this is like the one thing that, that nav mesh polygons need to have. They need to be convex. Otherwise, we don't know how to go around in those. Right. So if we want to move from one point to the other, this is like a small visual representation. Let's say we want to go from here to there. We have our graph. A star finds out which are the polygons we need to move through. And then we just move in straight lines. So I'm starting here. I know I need to move to this polygon. And I can kind of go in a straight line from here to, like close to the edge in the shortest way possible within the polygon. And then from here, again, I need to find my way to the other polygon in the shortest way possible. And I go over there, and then I move again between those polygons. And finally, when I'm in the final polygon, where the goal is, I just go in a straight line from where I entered to the goal. So see, we can always move nicely in straight lines. In reality, Unity does a little bit of more moving around. It doesn't go, completely straight line. But the concept is that, and then it just smoothens it out a little. Right. Does it make sense? Right. Very nice. So that's kind of it for nav mesh. That's a real concept. So just to give you a recap of what we talked about, you can see nav mesh as two things, two structures that are one on top of each other. One is the more concrete collection of the polygons, what we see in Unity, so all the polygons that are connected together. And the other one is the graph that they represent, which is more abstract, and that's the level where A star works on. So this is what we see in Unity, and this would be, for example, what we have in the abstract level. So something that just looks like this. It doesn't matter what, like the size of the polygons or any of that. It's just a graph with some weights depending on the distance between the two polygons. Or I think actually these distances are calculated from the center of mass of the polygons. I am not 100% sure right now, especially in the Unity implementation, but I think that's how it works. Right. So let's see. We are 10 minutes to 11. So I'm thinking we could do a break and then move on to pathfinding in Unity, or what? How do you feel?
Lunch break at noon,
We have a lunch break at noon.
and then we've got a break later on today.
Yeah.
Not necessarily a break in like full hour, like in the morning.
Yeah, and we have only an hour this afternoon, or?
There's an hour for lunch, and then there's an hour at
Okay.
o'clock.
Then I think let's move a little bit. Let's do another part here. This is more practical, and it should be, easier on our brains. So we just take a look at this, and then we'll take a break. Okay. So how do we do this practically in Unity? So in Unity, as I mentioned, there is this module called navmesh, which would make you think that it's a navmesh, but it actually is both navmesh and a star. So it's all combined under this navmesh umbrella in Unity, which is why sometimes it's a bit difficult to understand if you're coming purely from Unity, that there are two different things working inside this. It's not just like, for example, a lot of people think that navmesh is the navigation algorithm, but it's not. It's just in Unity, everything is called in one block. Perfect. So I have a file for you. Oh, sorry. Before we do that, I actually checked yesterday, thankfully, because I saw that you had 2023 installed, and things have changed in 2023. So it's a good thing I checked yesterday, because the process for building a navmesh is slightly different. Since the pre-2023, I'm going to skip it, but I'm going to leave it in the slides in case you end up using an older version, because to be honest, 2022 is not that old. It's not phased out yet or anything. So you might end up doing that. But for 2023, it works like this. I'll show you on Unity directly. I think that's going to be easier. So there's, let me make a small environment, then we have something to see. Let's take a plane, and let's put in something, put in a sphere, and a cube. There we go. Now we have something to play with. Let me just stretch this out a little bit, and maybe move it a little bit up higher. Right, perfect. Now we have a small environment that we want to navigate. So how do we find how to do that? So if you go into Windows, then in AI, where is it? It's a package. Oh, I thought I had. Oh, I think yeah, I guess it wasn't installed by default. I think I had it in my. Yeah. Okay, sorry. Then when I tried it yesterday, I already had the package installed and I didn't notice. But you need to install this AI navigation package. In the older versions, you didn't have to. It's pre-installed. It's an older version. It doesn't use. It works slightly different, but you didn't have to install a navigation package. So once you have that, now I think we should see it. Where is it? AI. There we go. Navigation. There we go. So this is the panel. This is the main panel. I usually like to have it here. I think I could see that we also have the obsolete version. So this one over here, yeah, I'm just gonna leave it here, is the old version, the pre-2023. As you can see, they're quite similar, but the new one is a bit more, it has less information. It only allows you to change the type of agents and the type of areas. The other one did a lot more other things, while now they've broken it up into different components. But just to take a quick look at what you can do here, in the navigation one, you can define agents. This is the basic agent. They call it humanoid. It basically tells how wide the agent is, how tall it is, what kind of height it can step on, so how much we can actually move up on steps, and what is the kind of slope that we are allowed to go on. So in this case, we can go up until the slope is 45 degrees. If it's more than that, we cannot. You can define as many as you want, because imagine you have a small enemy, a big enemy, a boss. They are all different sizes, so you need to tell the nav mesh how big these agents are. And for areas, you can do the same. You can create different areas and give them a cost. So imagine you have an area that is a swamp, and you would spend more time to go through that, or it would be more expensive. You can here basically say that, okay, this area costs 5, so that the agents will try to avoid going there if they can go around in a faster way. But once you have this, once you've defined these, and in this case, we're not going to define anything new, we're just going to keep the default, we need to create a new object. So if you right-click on the hierarchy, you go into AI, you should see that there is a predefined object called navMeshSurface. We'll just create that. And if we look at in the inspector, it just has one component, this navMeshSurface components, where you can choose which is the type of agent you want to use to build the nav mesh, or as it's called, bake a nav mesh. Not really sure why, but it's bake. And what is the default area? So let's see what happens if we press bake. Now we got a nav mesh on top of our environment. It's not very, it looks very simple because, well, we have a very simple environment. And you can see that it kind of bends up around here because I think it sees that you're able to jump this. Let's make this a little bit taller. So if I stretch it up a bit more, so it's more like a wall, then we press bake again. And now we can see that the nav mesh goes around it. We can see the polygons here, see the triangles. And we have a little bit of a nav mesh on top of there. So we have this area on top, which is walkable, but as you mentioned before, it's completely separate, right? There is no connection between that and other parts of the nav mesh. So we can't move between those. If we end up there for some reason, our agent can move around there, but it cannot actually do movement around that. And you can see that the sphere is something we can actually navigate because it's not too steep. So we can kind of step on it or just walk over it. Does that make sense? Nice. So yeah, that's kind of it. It's not like it's not that complicated. You just build your environment. You put in this navMeshSurface, and then you click bake. Done. Super simple, just as that. Not really anything else to do about that. If you want an object to not be walkable, because sometimes in the old version you had to mark objects that you could walk on as static. In 2023 you don't, so everything is considered to be a walkable surface unless you tell them not to. So I'm just going to show you that. So if I make another platform, I'm going to make another cube, and let's stretch it up a bit. So if I bake again, you can see that that also goes as a navigable part, because by default everything can be navigated. If I don't want this to be something where we can navigate, you need to add a new component. And the type is this navMesh modifier here. So if you can put that, you can tell it which agents are affected by this specific modifier. You can tell it what it does. And in our case, if we want it to not be walkable, you can say override area. And then we say not walkable. So we're saying this object is actually not something you can walk on. And if we go back to the navMeshSurface and we bake again, there we go. The nav mesh has disappeared. So we're all fine and dandy. That's not something we can move on anymore. Any questions? Does it make sense? Yes. Which one? Sorry, this one? Oh, yeah, of course. The slides will be shared afterwards, so don't worry. You can also get them later. If you miss something, you're not screwed. But this is the basic. Nothing else, super simple, not really a lot of stuff to do. I'm going to show you a couple of other things you can do with the nav mesh, but basically there's not much more to say. The other small things to show you is, of course, a nav mesh agent. So how do we actually have NPCs moving around? The only thing you have to do is to add this component to your player, to your NPC, to your enemy, whatever it is. Whatever you want to move needs to have this type of component where you can define which type it is. You can change some options, for example, how fast this agent is, how fast it turns, and so on. But that's basically what you can do. It's quite simple. And from the point of view of coding, so how do we actually tell an agent to go somewhere? It's super easy. We have one function to use, basically. There's more things you can do, of course, but to a level of actually making things work, there is one function. There is this set destination function that's part of nav mesh agent. So you can tell in your custom script, you get a reference to the nav mesh agent, you say dot set destination, give it a position, done. You don't have to think about it anymore. It just does it all by itself. So quite simple. Couple of other things. Obstacles. Sometimes we have things that can be in the scene that we want to stop the player from going through. For example, imagine that we have a door, right? A door that's locked, or maybe an enemy that's moving around and we can't really go through the enemy, right? We would want to go around it. So we want to have some ways to manipulate the nav mesh in these cases. So we can have this nav mesh obstacle. It's another component that you can put on an object. I'm going to just reuse my sphere here into, maybe let's call it a boulder. So something that can move, but we don't want to move through. We add a component, a nav mesh obstacle. And let's put it a bit higher. Let's rebake the mesh. And if you see here, right now, it doesn't look like the mesh has changed much. Because if you look down here, I didn't click this carve checkbox. So usually you would use this for example, enemies that are moving around. So the player will try to move through it, but if you get too close and you see it, and the player sees that, hey, there's actually something here, it will go around, but it will consider that a valid path. If it's, for example, a door that's locked, we do not want to go through a locked door. We don't even want to try, it doesn't make sense. Then you can add this carve checkbox, and it will just make a hole in the nav mesh. And imagine that then you unlock the door, right? Take it off, and then you're fine. Maybe even destroy the object if it makes sense, or move it around, something like that. But this way you can control whether the agent wants to try to go there, and then maybe change their mind if it can't, or if it really shouldn't even try to do that. Exactly.
Active or something?
Yeah, I think it's just, since it's a checkbox, I think it's just a true or false value. So you can just say navmeshobstacle.carve equals false. Done. Not carving anymore. Yeah. And the only other thing that's left to show you for this, and then we're absolutely done with the nav mesh, there's not really anything else to know, is that when we have things like this, where we have maybe islands that are unconnected, we can create links between those so that we have a way that the agent knows maybe this is a scripted place where you can go from one level to another, maybe by jumping down or maybe climbing up. You could maybe have a climbing animation happening as well in these cases. And there's two ways of doing that. Actually, I haven't checked how it is in the new version for the automatic one. Let's see. So let's see if I can find it. Oh yeah, it's right there. So you see these generate links button. If you click that, we should be able to generate the nav mesh links when it's possible. Usually they only go down, though. It's just from jumping off from something. Let's see what happens if we bake it. I think that this one is too tall at the moment, so it doesn't really like to even try to jump from there. Let's see if we can make it a bit lower if we see them appearing. There is a way somewhere. I am not sure where it is in the new version. In the old one, there was an option where you could say what is the maximum. It's an agent type. Yeah, right. Oh, there we go. Yes, you're right. Thank you for pointing it out. It's over here. So for agent types, you can see the drop height. So I think if we increase that by, I'm just going to put it very high so we're sure it works. We should be able to bake it. And there we go. Now we can see the links that have been generated. They have a small arrow. It's a little bit difficult to see in some cases, but you can see that the arrow goes only in one direction, so we can jump down but not up. Yes? So what if yeah. Yeah, I think that in the agent here, we can also give it a jump distance, so it's kind of like the other way. So we can define how high you can drop down and how high you can jump up. So I think if we erase this and we bake it again, no, it doesn't like it. I don't know. There's you're right. Yeah, I think you're right. I think it is that. Let's test it. If we move this over, try to move this over here and disable the nav mesh modifier. Looks a little bit too high, maybe. Yeah. Oh yeah, there we go. So that's the jump there. For jumping up, I think you either have to script it, or there is an option to make these links manually. So this is the way that it does it automatically, right? But if I'm just going to disable it for a moment so we don't have them there to see. But if you want to make one yourself, you can again go into making new object, and nav mesh link, there is like a predefined version of it. So you have this object that's kind of invisible, doesn't really look like anything. But you can define a starting point and an ending point. If you see here in the nav mesh link component, where we can say, okay, start from here, end there, and then we have a bidirectional connection, or if you want to, just a one directional. So you choose that yourself. And what kind of area it is. I think it was kind of easier in the older version, because here you have to put in the start point and end point manually, it seems. Oh no, you can move them maybe. I'm sure there is a trick to move these. I don't remember how, I don't know how to do it in the newer version, but you can probably move them yourself. In the older one, you could just have an empty object and use that as a transform to say starting point, end point. Which was a little easier, I think. But that's kind of all that we have from the point of view of the nav mesh. Then we can just throw in an agent, give it a nav mesh agent component, and we're good. But I think maybe we should take a short break right now just to make sure that we're not too tired, and I'll show you a practical example. In the meanwhile, while we have a break, I would ask you to try to get this Unity package I have, where we can play with it a bit. I have a link here. I don't know how we can share it to the chat. Otherwise, okay, perfect. Okay, if it's this one, I think it's the right one, because I have two, but I think this is the correct one. Try to download the file, and if it says something like navmesh, perfect, then that's the right one. So you can just make an empty project, open that package in, and then we have a small sandbox that we can play with later. Okay, but let's take 10 minutes of break just to decompress a moment. So the last part of today, or this morning at least, is I just wanted to give you some, like a practical example. So this is going to be a bit more interactive in the sense that if you want, we can do it a bit live coding style. So we just talk about it and we code it together on the big screen. Otherwise, if you would like to just have some time to work on it yourself on the different problems and then we take a look at them, that's also completely fine. So think about it for a moment while I show you what the concept is, and then we can take it from there. But first of all, if you've gotten the Unity package I sent you, and you loaded it up, it should look like something like this. Since this was made for the old version of the nav mesh, it actually, you can see that there is no nav mesh. So let's just do just very easily. We go like before in creating a new object of type nav mesh surface, and then we just click bake. And we should see now that our nav mesh has been baked into our game. I don't know why is it the player? Why is the player something that's blocking the nav mesh? Okay, interesting. Let's see if it works. So once you have that built, try to press play. And you should be able to click anywhere on the map. And your tiny player should go around and be able to navigate the environment. So that's kind of our starting spot, our starting place. Again, I don't know why it didn't.
Different layer.
Oh, it's in a different layer.
Make the player into a different layer.
Oh yeah, right. Because it's right in this case, like with the new one, everything is considered something that you can walk on. Right. Maybe we can do with the nav mesh modifier. Yeah, with the modifier, maybe we can remove object. Does that work? Yeah, that works. So to fix the player, you can just add the nav mesh modifier, and as mode, you say remove object, so it's kind of ignored by the nav mesh. So it just doesn't even look at it. And then you should be fine. So if you do that, then you should have a nice clean nav mesh where the player is not making a hole. You want to know what we did? It was just adding this nav mesh modifier to the player, and then changing the mode to remove object. That's it. Then it works. Then if you bake it again, you should be good. Yeah, it's because I noticed that it was making a hole in the nav mesh.
Yeah.
So we don't want that, right? It shouldn't make a hole, since it's something that just moves around.
Other like enemies would make holes, but you don't want the player.
Yeah, I think even the enemies shouldn't make holes.
Okay.
Yeah,
More,
because the holes are permanent, right? If I bake the nav mesh and there is a hole, unless I rebake it, that hole is going to stay there forever. Unless you use the carving thing that we saw before with the obstacle. That's the only exception to that. Yeah, yeah, but that's a bit expensive, so it's only something you should use when it makes sense. All right, then I hope this works for you guys. If it doesn't, let me know and I'll come help you in a moment. But I would like us to try to add an enemy now. So we have our player that we can control by clicking around on the screen. I would say just copy paste it. You know, we just duplicate it, make a new the player, and we call it enemy. So I'm just going to do that as well. Control D if you want the shortcut. So now we have our enemy. I'm going to put it a little bit further away from my player just as a starting point. And of course, we need to remove the player controller. Otherwise, we have two players that we can control. You can actually, if you want to test it, that works fine as well. If you start a game and then you try to click somewhere, now we simply have two agents that move at the same time. Of course, they find two different paths, but maybe it's not super useful, right?
If they meet up, then they stick together the rest of
Yeah, then they will stick together because then the best path is the best path for both of them.
It'd be a really funny game if you had the both
Yeah, yeah,
I control two characters running on the whole map.
definitely. So to avoid this, let's just go into the enemy and let's delete the player controller. Now the player control, we control only the middle one, and the other one should be separate on its own. And finally, let's make a new script for our exercise called enemy controller. So I'm sure you've done this a lot yesterday. Let's make a new C# script, enemy controller, and then let's put that on our enemy. Of course, right now the enemy controller doesn't do anything. It's just it's an empty script, but that's where our part comes into play. We need to put some code in there. So I think that our objective for this half an hour we have, or maybe a little bit more depending on when the food arrives, is to make the enemy move between points. So it's kind of like a patrol stuff, which would be fun. Then we can try, if we're done with that very quickly, we can try to make the player distract the enemy, so we disrupt the patrol pattern. And if we have time, which I'm not really sure if we do, we can try to also see, like if our enemy spots the player, then we can have them chase them. But let's see how far we can go. What do you think? Do you want to do it? You want to have some time to work on it yourself? Do you want to do it more live coding where we talk about it and we? Yeah? All right, so let's start with the first one, right? So make the enemy patrol between some points. How do you think we can start? You have any ideas?
Do we need to get the
Well, the enemy has the enemy controller script, right? So that one will know the position. So maybe the first thing we can do is defining what is the patrol path. So, where do we want to go first? Where do we want to go next? And so on. How can we define those? Do you have any suggestions? Yeah, I think we could use some game objects. Yeah. Yeah. Basically, we need to have a list of positions. So as you suggested, a list of vector 3 would be fine. Then we have the points. I would suggest to make it easier for us as designers, also, or for the designers that are going to put together the level, if we see ourselves more in the programming side. I would suggest that we use transforms and we use game objects to have these points around the space, because then they're easier to move around. So let's make an empty object. I'm going to call it patrol 1. And we have it over here. The thing with empty objects is that they, well, of course they're empty, right? So you don't really see them in the scene. They can be a bit difficult to spot. But you can add something called a gizmo. I don't know if you saw that yesterday. If you go here in the inspector, you see here where there is this kind of cube. If you click on that, you have some options, and let's say I'm going to click this blue icon, or, well, let's do red, it's a bit more obvious. Now we should be able to see it. Yeah, I don't know why it shows it only, oh, it's underneath there we go. So now we have a visual representation. That's only in the scene view, so it's not in the game. The game would not be able to see that, but at least it gives us a more visible point from our point of view when we're working on the scene. Actually, I'm just gonna move the game scene away so we have more space for this. Right, so let's say that this is the first point we want to go on patrol. Let's make a few more. I'm just gonna duplicate them. Let's do 4. Then we can do like a nice loop around the level. Patrol 2. Patrol 3. And patrol 4. let's move them around. So I'm gonna put patrol 2 over here in the other corner. Patrol 3 is gonna go over here in this corner, and patrol 4 in the last one. So in this idea, we're gonna have our enemy just basically go around the perimeter of the of our level. But of course, you can place these wherever you want. So it could be wherever you would like. Does it make sense up until now? All good? Nice. Then I think we can move on to the script. Oh, do I need to sign in with Visual Studio? Can I do it later? Thank you. Sorry, I forgot to try to open a script before, so now Visual Studio is being a little annoying. Let's see if it opens up quickly, otherwise we'll figure out a different version. Did you use a different editor yesterday? Okay. Let's try that. Okay, perfect. All right. Right. So as some of you was mentioning before, we need to have a list of positions, right? So now we have all of our objects in the scene. We just need to read them from our script. So I think we can make a list, public list of, I guess we could do game objects, we could do transforms, doesn't really matter. Let's do game objects. Actually, maybe it's easier if we just do transforms. Let's do that. Transform. Oh, I see the autocomplete is not there. So if I make some typing mistakes, let me know, since it doesn't show that. And this will be the patrol points. So if we go back to Unity now, and we look at our enemy, now we should see that we have this list of patrol points. It's empty. Let's say we want to have 4, as we actually do. And we can take our patrol points and drop them in, or like our game objects, and dropping them in there. So now our script knows what are the different parts that we want to go to. Everything all right up until now? Any questions? No? What's next then? What do you think? Yeah, right. So let's maybe try to just put the code to move to the first one. Then we can see moving on to the other ones, right? Do you remember how we can go, how we can tell a navmesh agent to go to a specific place? Yes? Set destination, exactly. But set destination is a method of the navmesh agent, so we need to get a reference to that, so because that's what we need to ask. So I can make a new variable called navmesh agent. And then we can do in start that we set it up. So we can say agent equals, and I'm sure you've seen this yesterday, we can use get component with the type we want to get, in this case navmesh agent. What, sorry?
Doing it this way?
Yeah.
I guess the core benefit would be that if you're spawning enemies, they can be assigned.
Exactly. We could also make it public and then just do it from the editor. But this way, it's kind of more automated. So if we just spawn something in, we're sure that it's going to be set up correctly. But they're both fine. Both ways are all right. Nice, good. And maybe let's just try to do it over here. So we said that we need to call set destination. And what is the first destination here? What should we put inside the parentheses? Patrol 1, but we don't have patrol 1. Not dot. It's a list, or it's the same as an array, right? So we need to use the square brackets. So the first element inside patrol points. And since that is a transform, we need to give, I think we need to give a vector tree. Correct me if I'm wrong, because I don't have the auto. Yeah, so it's probably something like this. I think we need to say patrol point 0 dot position. That should work. Let's see if it works. If we start the game now, okay. Yeah, not sure exactly what you're complaining about, but let's see if it works anyway. Yeah, there it goes. It goes there, and that's it, because we're not doing anything else. Okay, so what if we want to say, once you're close enough to this one, move to the next one, right? That's the next step. Any ideas on how we can check if we're close to a point? Yeah? Yeah. So in Unity, for vector trees, we have vector tree.distance that gives us the distance between 2 points. So we could say, for example, if vector tree dot distance, and then we need to say the 2 points, right? The first one would be the position of the enemy, so transform dot position. And the second one would be the position of the point we're going to right now. So it would be patrol points 0 dot position. So if that, if that is less than something, let's say less than 0.1, then we can say we're close enough, we want to move to the next one, right? So we can say the same as we did before over here for agent destination, but now we're going to position 1. That makes sense, right? I mean, we could do that, but it's a bit boring, right? Let's try to make it more universal or more general. Can we use a variable instead of these zeros and ones? Right, so maybe let's make a new int. Let's make it public so we can see it in the inspector, even if it's not that necessary. So let's call it current index. This starts at 0. So now instead of set destination patrol point 0, we could change this to current index. It's the same at this point. And maybe we have to change it over here as well, right? So everywhere we set 0, we say current index. And for this one, what do you think we should do? Yeah, current plus plus. If you want to do it in the line, it's a bit tricky because if you, I don't know if you ever noticed, but plus plus does the increase after the line. So if we say patrol points, current position plus plus, it would still be 0 and it just becomes 1 at the next line. You could do plus plus current position, which does it before, but it's a little bit tricky. I would just put it in front to make it clearer, right? So if we say current index plus plus over here, now we increase that, it becomes 1. And now here, we can just change this again to current position. Sorry, current index. So we're going, if we're close enough to the current one, we increase the index and we go to the next one. And we keep doing this over and over. What do you think happens if we keep doing this and we go up to 4? What, sorry? Exactly, then we can continue. We're just missing one thing here. We could do it with a modulo, but let's do it with an if just to make it as clear as possible. So we can say that if current index is more than patrol points dot length. Oh, sorry, it's a list, so it's count instead of length. So count gives the length, so that would be 4 if current index is more or equal than patrol points.count. Current index equals 0. So you see the logic? If it's 0, 1, 2, 3, we're all fine. If we go to 4 or potentially higher than 4, even if it shouldn't never happen, we set it back to 0 and we start again. Let's try to see if it works. Okay, it's going to the first one, and it's not doing much. Yeah, maybe 0.1 is a little bit tiny. Let's try 0.5. Yeah, like the object is also a bit large, so maybe it doesn't get as close. Oh, it's because it's higher, like the center of the object is a bit higher. Oh, there we go, that works. Now it's moving around. Very nice, seems to be doing it as we expected, right? Let's see if it manages to loop up with the last one. There we go, very good, perfect. And this is pretty flexible, right? If you want to add new patrol points or move them around, this is still going to work. You wrote the code once, you can use it as many times as you want. And as you can see, it was pretty short, right? It's like super simple code right here. Not really anything too complex. So I do like the pathfinding in Unity in the sense that they made it very easy to do, you know, like basic movement, and then you can focus more on the higher level stuff. Nice. So, well, before we move on, do you have any questions? Does it make sense, what we did? Perfect. What about the next part then? Let's say that we have a way that our player maybe, you know, let's say that it knocks on the wall, goes like this and makes the enemy confused or makes it think that, you know, we want to go there. What do you think we could do? How could we code that? Right. But we just need a position in reality, right? Yes? Yeah, I think that makes sense, especially if we look at the last part where we, you know, like if we want the enemy to actually see the player or chase it. But I would say let's maybe try to generalize this a little bit more again, or add an extra method. Let's make it public, and let's call it go to distraction. With a vector 3 as distraction position. Okay, what should we write in here if we want our agent to go there? Yep. Exactly, perfect. Actually, just distraction position, because that's already a vector 3. Okay, so that's easy. We could have the player call that on the enemy, and done. We have the agent going to the distraction. But what happens if, you know, like we actually want this to not be that the enemy goes to that position and then just gets stuck there? Can we put maybe something that allows us to go back to the main behavior, to the main patrolling?
Isn't it not
It would not, because
really too far from one of the actual points?
yeah, exactly. Because since we're far, we're just gonna go to our destination, the distraction. I get here, and then I'm done, right? Because I'm not gonna get closer to the next patrol item, so I'm just gonna get a bit stuck, not really do much.
We add another state.
Yeah.
Go back to your patrol.
Yeah, something like that for sure. Actually, as a question, I don't know, did you see coroutines yesterday?
See what?
Coroutines.
No.
Okay, then we'll just skip them. Don't worry, just because it's easy to implement this stuff using that. All right, but I think we need to kind of give a state to our player, right? We need to know when, to our enemy. We need to know when they are doing the patrol or when they're being distracted. Yeah, we could use an enum, of course. Since it's, it's either or, we could just say true or false, like a Boolean. But you're right, if we had more than two, then I would definitely use an enum. It would make sense. But let's give it another variable. Again, I'm just going to make it public so we can see it in the inspector for debugging purposes. Let's call it bool, and let's say distracted. So our enemy starts as being not distracted, and sometimes we might make it distracted. So if we're calling go to distraction, our player now is being distracted, is going somewhere. Let's save that information. So distracted equal true. Now the thing is that over here we had this behavior that worked really well when we were not distracted, but it doesn't make sense when we are distracted. So this kind of needs to go into an if. If we are not distracted, then this is the thing we want to do. We want to go on patrol. Just move all of this inside here.
Instead of nesting ifs, you also just do the and parameter. Not distracted at the end.
Oh, yeah, if you want to do like if not distracted and vector 3 distance, yeah, you could definitely do that. So that would also be completely fine. Else, if we are distracted, we want to do something different. It's a different kind of situation for our enemy, for our agent. So what do you think we could do to maybe say, if we have reached the distraction point, or maybe if enough time has passed, we would want to go back to being not distracted? That's kind of the concept, right? I'm going to distraction, maybe I'm gonna wait a moment, and then like, okay, there's nobody here, and I'm gonna go back. Yes? Mm-hmm. Very good, exactly. So I think we need to maybe save this distraction position again, because we're going to have to do something very similar to this. We're going to know when we get there, right? But to know if we're there, we need to remember where are we supposed to go. So maybe we need to add, I think we need to add a new variable, vector 3. Let's call it distraction target. And we need to save, when we get distracted, where are we going in there, so that we know how far we are from that. So over here we can also set distraction target to distraction position. And in here, we need to check if we got there, right? So it's actually pretty much the same code as this one. It's again an if, are we close enough? Then we want to do something else. So we can just copy paste this. Instead of the patrolling, instead we use the distraction target. And for now, maybe let's just say that we go back to the patrol. If you want, we can try to add a timer after that. It's not really that difficult. But let's say that we want to go back to the patrolling behavior now. How do we go back to the patrolling behavior?
We still have a current patrol point index that we could just revert to.
Exactly. So what do we write? Yeah, so we just copy that, and we do it over here. If we got to the distraction position, then we go back to the current patrol point. We just go back to what we wanted. Maybe you can do something where you also look what is the closest patrol point position, right? Then it would be maybe a bit more natural. You're like, okay, yeah, there's one right over there. I'm just gonna go there instead. But for now, let's start with this. Let's see, well, this kind of works, but we never call, oh, sorry, I think I forgot to write void here. So, sorry about that.
The downfall of not having the Unity linkage.
Exactly, then it's like some of these things that usually just go in automatically, kind of forgot about them. We need to call this distraction because we never really use it. So if you go on the player controller is the one that does this, that creates the distraction. So I think we can just add another if here in the update. So if input dot, I'm just going to use the right mouse button since we already used the left one for movement. So get mouse button 1. No, this is the old input system, so it works out of the box.
No. For the, do you import the
Ah, yeah, you're right, definitely. We need to figure out a reference to the enemy script to tell it to be distracted. So, have you seen how you can find the script from another, like an object that's somewhere else, further away?
You can search with the tag.
You can search with tag, exactly. So if we add a tag to our enemy, in this case, let's make a new tag, enemy, and then we apply that tag to our enemy over here. We can then say game object dot find game object with tag. Hopefully I'm not making any typos. Enemy. Remember that it's case sensitive, that tag, so you need to be a little careful with it. And then get component. And I think we called it enemy controller, right? Enemy controller. And then we can actually call finally the method that we wrote before into enemy controller. I do not remember how it was called. I'll call it go to distraction. Go to distraction, and what position would you pass on as the target? Transform position. Position of the player. Oh, this is not even looping. I hate this setup. Oh yeah, sorry. Thank you very much. It's a bit difficult without that. It's easy to make typos. Okay, I think we should have everything set up now because the player really doesn't need to do anything else apart that saying now be distracted. That's it. Let's see if it works or if we made some mistakes. Yeah, and so now the player went there, and I can distract it again, and it's coming for me, but I'm gonna sneak around. And now it goes back to that target. So now we have a nice, we can control our, or at least, oh, it's not working now. Did it get stuck? Oh, you're right. We never changed that. Thank you. Very well spotted. Yeah. So where do we put the distracted equal false? This one. Yes, very good. Exactly. Then when we go back to the patrol, we also say that we're not distracted anymore, and we actually go back to the proper behavior after that. So thank you for spotting that. Well done. Let's check again. So now it's going back, and yes, yeah, it's all working. Very good. Nice. Yeah, now we just need a cone of sight, and then I think we're pretty good at this point, because we have all the nice elements of a stealth game, right? We have an enemy doing patrols, we can do some distraction, well, we just need to be chased, and then we're all good. What do you think? Do you have the energy to try to do that as well? Or, all right. Okay, so last thing, how can we kind of define a cone of sight? What do you think? Yeah. Your idea is very good. There is actually a collide. I don't know if you probably haven't seen it yesterday, but there is this structure in Unity called a raycast, which is basically you draw an imaginary line or an imaginary cone or something, and you see if that collides with anything, if that hits something. So that's a very nice way of having these colliders that are not really there, they're not really in the scene, but they act as colliders that you can create on the fly when you need them. So that could be an option. We could just kind of like do that. We can also do it, I think, maybe we can do it more manually by just seeing what is the angle between, enemy and player. If the angle is small enough, so we're pointing in the right direction, and if we're close enough, then we can say that, yeah, we're kind of inside that. Yeah, basically that, exactly. I would be going for that just because raycasts can be a little bit tricky. They have a weird syntax, so I don't want to introduce too many things when we're just doing that. But let's try to just make it into using math. So let's see. That's the enemy that does this, right? It makes sense. The enemy is trying to look for the player. We could do that in update because we want to check that at every frame. Maybe let's do it before all the other logic. So if we find that the enemy does spot the player, then we can move on to the next, like to the different behavior.
So the first thing would be to implement the player object?
Yeah, right. We need to get a player object because we need a reference to that. Since we're going to do a lot of things with the player, I would get a reference in start or in using the drop down, the dropping menu in the inspector. We actually mostly need a transform. We don't really need, we just need to know the position of the player rather than anything else. So I think we can just make a transform instead of getting the whole game object. Not that it changes a lot, but let's do that. I'm just going to drag and drop it, so I'm not going to set it into in start, but you could also do that just as we did before with find game object with tag and so on. All right, so let's see. For angle, I think I need someone's help with this because I do not remember the function exactly. It's a function of vector 3 that we can use to check for angles. Actually, maybe I'll just Google it. Let's find the documentation. It's always your best friend in Unity. Actually, if you haven't seen it yesterday, I would really recommend always having the documentation open. For Unity, for once, it's actually pretty decently written documentation. So you can find a lot of information and examples just from there. So vector 3, let's see, public methods, angle, there we go. Right, so we can get the difference in degrees between the two vectors. Let's see, we also have an example here that shows us how it works. So we kind of want to do pretty much the same thing here. If the z-axis looks almost towards the target, yeah. So this is actually exactly what we want to do in the example we have here. We want to make sure that we're kind of looking towards the other, towards the target. So you know what? I'm just going to copy it because there's no reason to go and type it myself. We're going to have to change some names probably, but the concept is there. So instead of target, we called it player transform. So I'm just going to change all of that to that. Actually, just that one, really. And if the angle is small enough, then we can keep this and maybe print that, yeah, in sight, kind of. We still need to look at the distance as well to see if we're close enough to give it, because this would be even, you know, like if you're super far away, but you're kind of in front, it would still count as. Sorry, can you say it again? Yeah, it's the angle between enemy and the player. So if the player is in front of the enemy, we would trigger this. We should see that the player is inside. Otherwise, it will be, you know, if the angle is too wide, it will be further off. So we can control the, let's say, the width of the cone using this this value over here. This tells us, you know, like how large is this.
And is this just based on X? Like where?
Yeah, it should be just based on the
Object?
yeah. Yeah, because here we have in the first part, if you have done a little bit of vector math, player.transform position minus transform position means that we're basically calculating the arrow that points from me, the enemy, to the player. And then we just see the angle of that arrow that points to the player with the one that points straight in front of me. So if that angle is small enough, it means that the player is kind of in front. If it's too wide, then we're...
And is this here, it doesn't matter if you're on the left or the right side?
No, it's it should be normalized. So sorry. Yeah. Yeah, we're going to do the distance as well because this doesn't count distance. So it's kind of like a cone that's infinite in length. Let's just see if it works, just to double check it before we do the distance. So right now, the only thing that we should see is in the console something playing. Oh, sorry, I forgot to assign the player. So if you go into enemy and you go down to enemy controller, now we need to set this player transform that we created. So take the player and drag and drop it in there, over here. Then that error that came up should disappear. Very good. Let's see if I go here in front. Ah, there we go. You see that inside starts appearing. Now I collapsed it. If you haven't seen this, there is this collapse button in the console that allows you to basically put together all messages that are the same. And you can see how many times they came up on the side. So right now you see we're not inside, it's not seeing me, but now it went up again. Now that we're not inside anymore, it doesn't go up again. So it seems to be working fine. We just need to add the distance as well now. I would say that for that, well, we already know how to calculate distances, right? We did that before. So we basically have to do the same. Just gonna copy this. So we can say if the angle is less than something and transform dot position, the distance between transfer dot position and player transform dot position is less than something. Let's say, I don't know, 10. Then we should be inside now. So now it's not forever, but only if the distance is actually something that makes sense. So we have a proper cone of sight done. Let's try to check if that works. I don't know if 10 is too big for this map. It might be, it might be that we don't really have more than 10 in space, but I'm gonna try to go here as far as we can. Let's see. Oh no, it's pretty good, right? It was like halfway through the map, more or less. Because if you look next time that it comes around, I think it started seeing it more or less around here. So in the first part we don't see it, and then it starts to come up.
Because your players told
Yeah, yeah. So that looks pretty good. All right, we have one last thing to do. Now we know how to find the player. We have made our cone of sight. We just need to make the enemy chase our player. Exactly. So that's pretty much what we want to do. Let's make this into a larger if. It's definitely not the right way of saying it, but and then we can say the same set destination that we did before, but this time with the player. Set destination, player transform dot position. We don't really have a way to get out of here now. So if we see the player, it's basically going to chase them until it reaches the point where they are and stop there. I think that means that if we go out of line of sight, it will break. It will just stop in the last place it's seen the player and not do anything else. We could do, basically we have to do something similar to what we did with the distraction before to maybe have a timer or something like, right? So if I get to a point and I'm not seeing the player for X amount of time, I go back to the patrol. So we would need to have another if with a timer or something like that. But let's try to see how this works. Okay, so I'm being chased. Yeah, now it lost sight of me because I turned the corner a bit too fast. Let's see if we get back inside. I think it should chase us again. It's not very good. It turns very slowly, so it's really easy to avoid it. If you want to try to make it a bit more reactive, you go into the enemy, and down in the nav mesh agent, there is this angular speed, which is how fast the agent actually turns around. So if you turn this up a bit more, I think we should have it should be better at chasing us, because it's able to turn around and deal with corners a bit better. No. Oh, actually, no, yeah, you're right. It can see through walls. Yeah, you're absolutely right. It can.
the cone's wide enough in theory, it would just see you everywhere.
Yeah. Yeah, that's why using a raycast would be better, because that would take the walls into account, since it's actually a collision. Yeah, but we haven't done it. We haven't done it this time. If you want, just try to search for raycast in the documentation and take a look at that. There are a lot of ways that you can make that work. But yeah, now it gets a little bit stuck when we do this. We can do the distraction to kind of get it to chase us again and get outside of the loop. What, sorry? Yeah, exactly. Like if we bring in there, then it's like, oh, this is a patrol point. That's nice. I can continue now. So it's not a perfect code, right? We have some issues and some kinks to smooth, but at least we have something working in a pretty decent time, I would say.
If we wanted to just put a sim in there, could we access
Yeah. For you mean you,
You have to access, a lot of the times you have to access speed to know when to trigger them, right?
yeah, like to see like the speed of the enemy. You mean?
Yeah, if it stops moving, you're like, okay, so if it stops moving, go back to control position.
Yeah, yeah, that's a good idea. I think you might be, you probably would need a timer as well, because it might mean, you know, like maybe if I'm doing a very sharp turn, there's going to be a moment where I'm, exactly, where I'm going to be a very slow speed. If this is, does it have a rigid body? If it has a rigid body, you can access it through that. Otherwise, yeah, but that is the speed, how fast it goes, yeah. I think there might be a way to access the current speed in the nav mesh agent, but otherwise, usually you do that through the rigid body. So you could add a rigid body, also make it, you know, not responding to forces, to gravity, and then you can access the speed from there.
And then we would just do like a statement where it's like, yes.
Yeah. 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 I would super much recommend you guys to look into coroutines. It's there's basically special functions where you can stop the execution midway. So you can say, I want to do, usually, you know, like if we call this go to distraction, right? We have to do all of that in one frame. Or the same for update. Update happens every frame, but we need to go from top to bottom, all of it every frame. Coroutines are something where you can do a part of the function and then stop, and then continue later on, like maybe 10 seconds after, or when some condition comes back. So it's a bit of a special way of coding things, which is super useful when you want these things in cascades. Coroutines. Coroutines, yeah. It's a special thing for Unity. It's kind of like Unity doesn't allow you to use threads, which is the way that you would normally do this kind of async stuff. Or you can, but it's a bit tricky to make them work. So it's kind of like a workaround that Unity found. But that allows you to make these kind of like behaviors where you want to wait for some time very easy, because I could say I start a function that deals with distraction. I try to go to the distraction. I got to the distraction, good. Now I'm gonna just wait some time and then move on to the next part, which is I'm gonna move to something else. Exactly, because here we have to use a lot of ifs, we need to use timers. With coroutines, you can get around all of that. Your code looks a lot cleaner, and they're really powerful, they're really interesting. So take a look at that. I don't think we have time to, to go into that, sadly, but they're a super powerful thing to use within Unity. And they can make, you know, writing even this kind of code so much easier. Right, but I think it's 15 minutes past 12. I think the food should also be arriving soon, so let's take a break and we can continue later. I think we already did a ton of stuff today, so thank you guys, and we'll continue later. What we did before, I'll make sure that we get the scripts that we wrote shared with you guys afterwards, but I've also have some other possible solutions in the slides, doing things a little bit different. Like here we have the patrol positions done as actual vector trees, but I think the one we did is much nicer than this in the end. So there's a couple of other options, but more or less is what we did. Oh, actually, this searching for the player part is using a coroutine that I was mentioning to some of you. So you can take a look at this later if you're interested. But the main difference is that this function doesn't really run in one frame. But this yield return null means wait the next frame and then continue from that exact point. So this loop, this while loop, doesn't just run continuously, but it just runs once every frame. But again, take a look at that. It's a really cool thing that you can use in Unity, but we won't really do much more than that. So we're moving on to the topic of the afternoon. So today, in the afternoon, we're going to talk about how to model behavior. So we're going to talk about a couple of different techniques that are kind of standard in the industry. The first one being finite state machines. And I'm sure you might have heard about it. I think that one of the classical myths about game AI is that it's all about controlling NPCs. Today we are actually just looking at this part, but I just wanted to mention this because there's a lot of other really cool stuff that you can do in games with AI. If you think about procedural content generation, games that have generated levels, think about Minecraft, right? If you want a very classical example. So don't think that this is the only thing that we have in game AI. There is a lot of more stuff, but today we're just going to focus on this. I just wanted to tell you that it's not all that. The other thing that is quite of a myth when you think about game AI is that a lot of people consider that as we want to play the game as well as possible. And that's definitely a part of it. Think about bots that play chess or more recently Go and so on. All of these are really cool stuff where the objective is to create a superhuman player that's much better than all of us could ever be. And of course, in some cases, that is actually possible. But don't think that's all there is to it. I think there's also a lot of interesting stuff going on in trying to make players, AI players that look like human, for example. So they're not playing the game the best they can, but they're playing it in a way that's more convincing or more interesting for the player. Because, think about it. If we're playing a game and our AIs are just so much stronger than us, it's not going to be fun to play this game. It's interesting from the point of view of computer science, of learning something about the games, but it's not fun for us as players. Definitely not. So there's a lot of interesting, cool stuff going on in that as well. So what do we need to control an NPC? We already saw something about that this morning, about movement, pathfinding, so figuring out how to make an NPC move around. The next part, the next step is to learn how to act. So how can we define how our agents are going to do actions, are going to behave differently in different situations, and so on. Animation, of course. And potentially more high-level planning, like tactical, meaning where you have more than one agent working together, strategic when you go even at a higher level with multiple sets of agents that need to coordinate things. Today we're going to focus just on acting for now. Well, actually, for all this, but just so you know, there's more things that you can look in. But those two are, the top two are definitely the most useful one, the ones that appear in almost every game. So classical solutions about all of these, movement and path planning, we already talked about it this morning, A-stars, nav mesh. Other things that could be interesting if you want to look them up are influence maps or flocking and flocking. For acting, we're talking finite state machines, which we're going to talk about today, and also behavior trees and decision trees, which I hope we're going to have time to talk about today as well. We'll see how much we can fit. I have slides for all that, but we'll see what we can do. If you're interested in looking at the other ones, we're not going to look at them, but there is this technique called goal-oriented action planning, GOAP planning, which allows you to build more kind of squad behaviors. This was made actually quite popular-ish. There's not that many games that use it because it's a bit more expensive, but in the game Fear, if you have ever heard of it, that had some pretty interesting, more complex enemy behaviors where they, for example, would be able to flank you and coordinate things between each other, and they use that technique to make that kind of planning for squads. Of course, you also need to put these things together. So if you're interested in seeing how you can put all these techniques together in ways that make sense, take a look at those two techniques. You can Google them and find out something about them. But let's move on to finite state machines. I made this meme because I think that it's so typical in games that finite state machines are everywhere. We're going to see a bit more about how they are, but if you think about any game you can think of, it's 99% there's going to be finite state machines in there, probably to control the enemies, maybe to do other things, but they're everywhere, absolutely everywhere. And I think it's a bit limited from the point of view of game developers that this is kind of the go-to technique. We'll see why I think this a little later on. Maybe you'll agree with me, maybe not. We'll see. So what are these things? It's a way to formalize the internal state of an NPC. It's super common, video games. It was there in Pac-Man, so you know it was there from very early days. QuakeBox, FIFA, Warcraft, again, any game you can think of, it probably uses finite state machines in one way or another. The concept, as you can see from the name, finite state machines, is that we have some states. They are a finite number, so there's not an infinite one. You have to define before I'm going to have state 1, state 2, state 3. Patrol, chase, get distracted, in the example that we did before, for example. And then we need to say, how do we transition between these? What are the conditions that make me go from one state to another, and so on? So it could be something like this. For example, it can be in all kinds of shapes, right? But we have a state 1, we have a state 2, we have another state. We know that we start in some specific state, and then depending on what kind of conditions get triggered, we move between this. And again, it's a graph, right? We're back at graphs. They keep coming up all the time. So now let's just move on to something more fun and more active. Can you come up with a finite state machine? So I'm going to give you some time, maybe 5 minutes, talk about it in groups or on your own if you want to, and try to come up with one. Remember, states, transitions, you can do whatever you want. It's up to you. Make your fantasy come up, or of course think about some games and see if you can see what kind of states there could be there. Right, go. Right, 1 minute left. Start drawing your finite state machine if you haven't done it already. All right, time's up. Can anybody tell me or describe to me one of your finite state machines? I will, for the sake of the stream, I will dazzle you with my paint abilities in trying to recreate that in the meanwhile. Yes? A what, sorry? Oh yeah, nice, yeah. Yep. Yep. Yeah. Very nice. So we have jumped on to go in one direction here, otherwise we're going into the, like after some time, we go back to walking, and then you said that we have another state of like sliding or, yeah, sliding, where we can only go in from the shell, right? But if you jump on it again. That is true, very good point. So we have, our finite state machine looks something like this. So jump and then jump again. Actually, I guess this could be just one transition with like 2 points, since it's kind of like the same condition. Oh yeah, jump or kick, you're right. Yeah, it's a bit difficult, it's a bit tricky for that. Very nice, awesome. Cooper finite state machine, very nice. Anybody else has a finite state machine that they want to tell us about? No? Yes? Mm-hmm. Yeah. Yeah, like I don't remember, I don't know exactly how that could be, but there was, it's definitely something like where we have a state of spawn zombies, spawn, they also can spawn some special ones. And there was also like sometimes there's like a huge horde that comes all at you in one spot in one place. But it also does spawn health kits and stuff like that to help you. So there's also that as a possible option. Yeah, that's true. That's true. Yeah, so we have a lot of these. And the transitions here depend on how the players are doing, basically. So I'm not going to draw them because it's, maybe it's going to be a bit too much. But for example, after some timer, the cooldown goes into probably spawn some zombies. If they see that the players are doing too well, then they might go into spawn special zombies. If the players are still doing very well, they can spawn a horde. It's a bit more complex than that in Left 4 Dead. I don't know exactly how it works, but it's a super cool system, by the way. So if you haven't played it, try to play it and try to pay attention to what happens in the game with when things start to spawn and how they appear around, because they do some really smart stuff there. Right, very good. So, well, that didn't take a long time, right? It was pretty simple. So that's one of the reasons why finite state machines are so popular. They're everywhere because they're really easy to come up with. If you see, this is another example for here. It's super simple. The other thing that's really nice from this is that designers understand these. You know, you give this, a designer can come up with these without knowing anything about programming. Give it to you, the game programmer, and be like, this is the behavior I want. You can code it. I mean, maybe sometimes you're like, this is really not really something that we can achieve. Maybe there's something impossible, but they can come up with ideas that usually make somewhat sense. So it's easy to understand. Also from people that do not know anything about programming or artificial intelligence. It's kind of a script in reality, because all of this, all of the intelligence from this comes from you, or the designer, or whoever comes up with them. There's nothing about this that's automatically fixed by the AI itself, by the bot. It's just you, it's just us. Where can we use them for? You might have noticed, if you're a bit more familiar with Unity, if you have ever used the animator in Unity is a finite state machine. So, you can use that to say, this is the animation to be played. If something happens, for example, if the player jumps, we're going to play a jump animation. When the player lands on the ground, we're going to go back to the idle animation, and so on. So you can use it for that, for example. You can use it for NPC behavior, as we were talking about. You can use it as a game logic controller. For example, imagine that you have a game that's set up in rounds. You can have start game, round 1, then the round ends, maybe you go back to another round if you have enough rounds to be played, until you reach some kind of ending and you go to a final state of the game. So you can come up with a lot of ways of using this. It's not just for NPC behavior. You could use it as an input manager for the player, many other things. Pretty much, it's a super flexible type of structure. You can use it for a billion things. How can we implement them? Actually, that's also another reason, I think, why it's so common everywhere, because it's super easy. The simplest way is just if statements, right? If I'm in this state, do this. If I'm in this, else, if I'm in this state, do that. And then just some transition somewhere where you just change the state variable. And that's it. You're done. Nothing really too much to do. The only thing that I would warn you about here is that with if statements, it can become not very readable quite fast. Yes?
Does C# have switches and cases?
Yes. Yes. Switch case. I hope that you know what a switch case is, otherwise I have an example later to show you. It's a kind of a structure in a lot of programming languages to make this kind of lots of if-else cases collapse into something more readable. And you can use that. It's a lot more understandable. It is better. But both of these can get messy quite fast. So if your finite state machine is small, no problem. Just go with this because it's the easiest way. But if you want something more complex, then it will become a bit more difficult to read or to maintain after a while. And it's a bit hard to reuse because they just become these boxes where you can just take out a state and put it somewhere else, or it's not very easy. If you want to have the more flexible one, I think, is to have each state as a class. Then it becomes more complex. You have a lot of more overhead in how you have to write down the code, but it's a lot easier to reuse. You can just, if you made a patrol state, You can use it in one finite state machine, you can move it into another finite state machine or another one, even in a different project and so on, and keep using these. So it becomes easier to use. But there is a lot of complexity that you have to put on top of that before. So let's see a couple of examples. I think we need to share another QR code here. Let me find it. If you're here in class, I think it's this one. You can just scan it. Otherwise, if we can put it on the chat, then it should be easier to get. But hopefully that should lead you to a file called FSM examples or something like that. Perfect. So it should be in the chat now. If you can get it from there as well. And if you import that, you can either put it in a new project or reuse the one from before. Then you should have a folder called FSM implementation in the root asset folder of your project. And if you look into that, I have left the README, so there is some information if you want to take a look at it later as well. Then we can see I tried to implement the simple input manager in all the 3 different versions, or at least in these 3 different versions of how you could write an FSM. We can take a look and see how different they are between each other. If you open this, the scene FSM test, you should see this. Actually, I think I don't know if I taught it more of a 2D environment. If we try to play it, there isn't really much happening here. There is just a space button that makes you jump. And there is a C button that makes you crouch in this kind of weird, janky way because I just wanted it to work. Wasn't really making it very nice. And if you crouch while you're jumping, it's a bit difficult to see, but you get a force applied down, so you can do a bit of a dive. You go down a bit faster than just when jumping. So those are the 3 things you can do in this. It's very limited, but those are the 3 inputs. You jump, you crouch, or you dive by jumping and then crouching while you're in the air. So let's take a look at the implementations, if you're ready. If you go to the player script, the player game object, you can see that it has 3 different components, V1, V2, and V3. For now, V1 is the one active, so let's take a look at that one. So this is implemented with kind of implied finite state machine. It's similar to what we did before with the patrol state and the escape, the patrolling and getting distracted and chasing. Pretty much the same concept. You see here we have 2 variables, 2 booleans. Is the player jumping? Is the player ducking? Not really much is happening here. So if we press space, if we are not jumping and we're not ducking, then we jump. Otherwise, if we press C, the crouch button, if we're not jumping, we duck. If we are jumping, we set is jumping to false, and we add this force that makes us go down a little bit faster. Otherwise, if we release the C key, so we let it go, and we are ducking, we're just standing up again. These 2 lines here just kind of squish the model just to give this impression of being crouched or not. And then the only thing that's left at the bottom is just a check of collision with the ground to change the is jumping variable. So if we touch the ground, we're not jumping anymore. When we leave the ground, then we're jumping. Does the code make sense? Do you have any questions? So it's pretty simple, right? It's not that complex. For this kind of implementation, for this problem, I would say this actually is plenty. It's enough. But it is a bit confusing, right? I explained it to you, but I think if you were to just read it from scratch, you would get there. But there isn't really anything that tells you exactly what is going on. It's like, oh, okay, if I press a space key, then I'm gonna do something if something else, some of these variables are not on. So it's a bit difficult to read. So let's try to take a look at version 2. Version 2 is the one with the switch case. So now, instead of having those two booleans, actually, let me see if I can put it side by side. That would be nice. No. I don't remember how to do the split panel. There we go. Okay, so now we can see here we have V1, where we have these two booleans to tell us, are we jumping, are we ducking? Here instead we change to having a state. And I use an enum to define what states are. I think I defined it down here. So now it's clear we have these 4 states. Instead of just having these variables here that are maybe true, maybe false, now we know that either we're standing on the ground easily, we're jumping, we're ducking, or we're diving. So we're in the air and then we're going down. So we have 4 clearly enumerated states. And we have this current state variable that tells us, where are we now? What are we doing? So now the update, instead of being this mess of ifs, becomes just a nice switch for that current state. So we can see, if we're standing, these are the things I can do. I can either jump, press the space button, and then I'm jumping. And see that here we change the state. When we're jumping, now we're saying, now we're not standing anymore, now we're in a state of jumping. In the next frame, that's where we are. If we're pressing C, then we're gonna switch to ducking and so on. And then in case we are jumping, we only have one thing we can do. We can only press C. We actually, we're not reacting to pressing the jump button because it doesn't make sense. We're already jumping. So we don't even have to do these checks of, if I'm not jumping, then I'm gonna do something. And then we have a state for ducking. In reality, the state for diving actually doesn't do anything in this, because it's just, you're just going down. You're not doing anything else. So you can't really react or do anything when you're ducking, when you're diving. But it becomes a little bit clearer, right? Now we have the code separated by function. This is what I can do when I'm doing this specific thing, when I'm in this state. This is what I can do when I'm in the other state, and so on. What do you think? Do you have any questions? Does it make sense? Yes, of course. This one? Oh, this one, the collision? Yeah, so this is a collision with the ground. So if we are in the state of diving, or in the state of, I don't know why this is, or in the state of jumping, and we are colliding with the ground, then we're not jumping anymore. We're standing, because we are now on the floor. So that's why we have this. In the other one, in the other version, we're just changing the is jumping variable to false. Now we're just saying instead the state is that we're standing, we're on the ground. I think this is already much better, but I don't know, the programmer in me doesn't like it too much as well. Maybe I like doing, I like object-oriented programming a little too much in these cases, because I think there is a lot of, it's still not super clear what happens when. Because for example, take a look at this. So when we are jumping, when we press C, we go into the diving state, and we are adding this force down. But to me, this force down seems more related to the diving state rather than the jumping state, but it's inside that, right? So I think that there is something there that I don't like too much. I would actually like that for every action that's related to a state is actually connected to that specific state rather than being a little bit more mixed like it is now. Oh, and thankfully my delivery of coffee is here. Thank you very much. Everybody will be happier with this. Good stuff. All right, so let me show you version 3. By the way, if you want to try to test them, you can try to just, enable and disable them. For example, here, if we use version 1, as we were seeing before, you can see the two variables changing when we jump and when we move. So if you look at these two, you can see when I'm jumping, that triggers. When I'm ducking, that triggers as well. But if we change this and we go to, wait, why are they all on now? Okay, let's try to activate version 2. Now with version 2, we can see the state there changing between the different ones we have. So it's also a little bit clearer from the point of view of debugging. What are you actually doing? See, if I do the crouching while jumping, it actually shows up the diving state. So I think it's a little bit easier to understand than just having a ton of these variables lying around, because this is a pretty simple finite state machine, right? If it was bigger, we would have to have a lot more of these Booleans. Let me show you version 3. It's a bit more complex. So I hope I'm not going too far. I don't know how much object-oriented stuff you've seen. So please stop me or ask me questions if you think it's a little weird or you don't understand exactly what's happening. But here, instead of having, for example, that one current state, we are defining a new object for each state. And now the current state becomes one of these type of objects. Let me just scroll down a bit so we can see what these are. So I define this, a class for the player state, which is abstract. Just to remind you, in case you haven't seen it, an abstract class means a class that can't stand on its own. It's incomplete. So it's more of a definition of something. So here we're saying that player state classes need to have an enter, exit, and an update function. But we don't say how they work. See, we have no body. There's no curly brackets with actual code inside. We're just saying we want that to be there, but we leave it up to you to implement it. And then we can define, for example, a standing state, which is inheriting from player state. So it's a type of player state. And now we can say what happens when we enter the state, when we exit the state, and when we want to do an update, so each frame, basically. So you see how we have separated actions that happens just once when we start the state, just once when we get out of the state, and at every frame of the state. Does that make sense? All right, good. Just to show you some of the other ones, for the ducking state, I think it becomes more clear, because for this standing state, we don't really do anything special on enter and on exit. We're just kind of waiting to move into one of the other states. But for ducking, it becomes more interesting. Now, we have clearly said that when we enter a ducking state, we squish our model. When we exit the state, we expand it again. And in update, we can only wait for a release of the C button to go back to normal. So all of the functionality of the state is encapsulated inside the state class. It's not kind of like mixed around in the switch case between the states. It's all in one place. And the same concept goes on for the others. So we have the jumping state where when we enter, we actually do the force adding to jump. If we look back into the version 2 for this, just to show you the difference, where do we actually do this? we are doing it in case standing. See, in case standing, if we press the jump button, we actually do the jump. But it's kind of, I don't like that, right? Because it is in the wrong state, logically wise. Well, in this case, we have it all nicely encapsulated into the right state. And I made this diving state a little bit more complex. I don't think I'm going to go into it now because I wanted to show you that it can be a little bit more, you can actually put a lot more meat into this and make it more understandable. For example, I'm not going to go too much into it, but here I am checking when we start the diving, and if enough time has passed between the start and the end, we're saying that we're doing, for example, a ground attack. So all of this kind of information can be put in also with specific variables that are just for that state. They're not part of the player itself. They're not part of any of the other states. They're just of the state that makes sense, that it has that. Going back a little up to the actual player, because these were all states, how does that change? Let me go back to the top. As we said before, here we create the states, which also means that we can create them anywhere else. They don't have to just be states of the player. They can be states of whatever script. We can do the same thing everywhere else. We still have a current state, but it's one of these type of classes. And when we want to change state, we use this method change state that I wrote, where depending on the state passed on, we can go to one or the other. And the most interesting thing is that we call the exit. When we move from one state to the other, we exit the first one, then we enter the other, so we can do all of these start and ending behaviors within states. I think that's kind of it. You see in update, I'm just calling the update of the state that's currently active, so that we're basically passing on these what we want to do with each frame to the states themselves. Okay, I'm sorry, I feel like that was a lot. So if you have any questions, of course, let me know. Yes? Yeah. Same frame. Yeah. If we want to follow how this works with the frame, right? Let's say we are in the standing state. So frame starts, we get update running. We call update of the standing state, the current one. So we go down to the standing state, where we execute this code, and if we have pressed jump, then we're jumping. Yeah, we're calling change state, which will then call the enter of the jump state. So it all happens in one frame. So in one frame, we do the out, we do the exit, and we do the enter of the next one. I guess you could put a break there, like you could make it like do the exit in one frame and the enter in the next frame, but I guess it depends on what they're actually doing. In this implementation, enter and exit happen at the same frame. And if we look at this from the point of view of the game, if we turn that on, you know, from the point of view of actual working, it works the same. So you can see how it might be a little bit weird thinking that we need to do a lot of different, like make all of this big skeleton for achieving exactly the same. But the point is that it becomes more reusable. So if you think you're going to reuse things, consider doing it this way. If it's a one-off, simple finite state machines, the other two methods are totally fine. You know, it becomes a waste of time making something this complex with an architecture, with the architecture behind. But just to show you, for example, here, we can see the ground attack if it works. So if I press C when I'm kind of up, we get the ground attack because enough time passes. If I wait until we're very close, then we get this not enough time. So we can build all these kind of more complex behaviors inside the states in a way that it doesn't become super confusing because you don't have everything kind of mixed together, meshed in one block. Right, then, unless you have any other questions, I think we can move on. I know this might have been a bit of a lot, but I'll share you, of course, you have the code, take a look at it, and if you have any questions, of course, you can let me know also after class. I'm sure I'm sure we can share my contact with you. Just again, as a final thing, which one should you use? Remember, it just depends on your problem. I like this, the last one, because the software engineer in me likes when things are all neat and nicely put together. But to be honest, if your problem is simple, go with one of the other ones. It's a lot more easy, and you don't have to build all this architecture with classes, things that inherit from the class, and so on. There was a lot of empty space in this one because we have a lot of these exit and enter variables that are functions that are empty, they don't do anything. So if your problem is simple, don't do it this way. But if you want to build something that's more complex with a lot of states, a lot of complexity, then I think this is a better way. Just to show you a couple of things that you can also do with finite state machines. This is from an old thesis at my old university when I did my master, but it's actually something that you can see sometimes in the industry as well, where you can have finite state machines inside finite state machines. I think you can do that with the animator as well. You can make these states that have more complexity inside, because it's a bit difficult sometimes, as I mentioned, to have finite state machines with a lot of states. You could have, let's say, this alerter state that has inside itself smaller finite state machines to control what happens inside that. In this case, actually controlling two different parts of the player body, the upper body and the lower body. So, kind of like the movement function and the aiming, more acting function. So you can do lots of interesting things with finite state machines like this that go a little bit outside of the norm. So finally, just to conclude with finite state machines, why should you use them? They're simple, they're predictable, and they are debuggable. They're scripts, you can debug them as any other piece of code that you write, super easy. If something doesn't work, you will likely be able to find out where and why. Why not finite state machines? Why I think they're a bit, why I think we could do more? They're predictable. It's a good thing because the designer will definitely want things to behave the way that they designed them. But after a while, you get really, you will understand as a player how they work. I like the example with the bokoblins in Breath of the Wild because they have a pretty complex behavior system. They can react to a lot of different things. But after a while, you find out the patterns, and then you can see that they're always the same. If you do something, they will react the same way every time. So I think that can get a little boring, especially in games where you expect players to stay there for a long time, or in big games. The other thing is that it doesn't scale well. As I mentioned, the complexity of keeping these things together or understandable when you have a lot of states is really a problem. If you imagine writing this with 100 states, it would be insane with us. It would be a mess. Super weird, super difficult to maintain. So it doesn't scale very well. And the last thing is that the agent never learns. Again, this is a script, right? We decide what happens. We define all the behaviors, how they move between each other. There's never any learning. If you find out that in some ways you can easily game the NPCs, they will always do that. They will never learn how to get around it. So I would say that's kind of, the problems with that. Yeah?
Mark, I challenge you on, I think,
where because they are predictable and the agents move around that, it allows you, after playing the same level multiple times, to and a player that's been doing this like 30 times, it's the very fact that they are
Yeah.
that allows you.
I think it's a wonderful point, and it makes a lot of sense. I think it really depends on the game, right? There are some games where you want that to happen. As in the Hitman, you're exploring a level with a lot of different agents that interact and do things. So it makes sense that you want something that's reproducible, because you are in a way learning about how the level and the NPCs work together. I think in some games that's perfectly fine. In other games, I think it could be more interesting if they could change the behavior, because again, taking the example here of Breath of the Wild, the enemies don't do any special thing. There is nothing really interesting from learning how they, or at least there's something interesting learning how they behave at first. But when you see that they always react the same way, it becomes a little boring, because they're just kind of random encounters. They're not characters with like a schedule or something specific to do. But in any case, I like finite state machines. I'm not against them. I just think they have some good things and some bad things, and it always depends on what's your objective. All right, then I think that's it for finite state machines. Do you have any final questions before we move on? No? Perfect. All right, then let's bring it one step up, I think, because finite state machines are nice, but let's see what else we can do. This is also a technique that's pretty common in games, maybe a bit less than finite state machines, but I would say that they do appear once in a while. So decision trees look like this. While finite state machines were graphs, these are trees. I hope you're somewhat familiar with the structure of trees or how they're made, but basically it's kind of something like that, where we have a starting point and branches that go down until we reach some end, in like the most simple way that we can describe a tree. It's a flowchart. So each internal node, so the ones that are not at the end, are questions or check some kind of attribute. And then the leaf nodes, the ones at the bottom, the ones that don't have anywhere to go, are actions, some decisions that the agent can do. So yeah, something like this. For example, we need our agent to decide what to do, right? We can check, is the enemy or the player nearby? No. How am I doing with health? Should I go and get some health or not? And we just keep doing this until we reach one of the ending points and we decide what to do. So it's pretty simple, right? It's not really that much of complexity going on. One of the cool things about these ones, one of the things that I really like compared with finite state machines, is that these can be learned. So if you collect some data, you can actually learn the behavior trees, the decision trees out of that data. So imagine that you have some players playing your game for a while. You collect a lot of information from them, how they react, what kind of things they do in what kind of situations. You can take all of that, you can crunch it, and get something like that. So this would be, for example, a way that you can have an agent that's not just something that you have coded beforehand, but something that behaves like your players, or like some specific subset of your players, for example, which could be useful, could be interesting. Maybe it's just something that you do to understand your players. Maybe you don't even put it in the game itself, but it could be something useful to kind of understand how your players play your game. Another good thing of this, just like with finite state machines, it's humanly understandable. You can also ask your designer, hey, write me how you want the NPCs to behave. They can make a flowchart. I think most of us can without too much problems, whether we know programming or not. So that's also a very nice thing. I would say the main negative things of this is that it's reactive. If you think about finite state machines, before we had states and we did things depending on the state. In this case, we don't have any states. if I'm finding health one step before, and then I go back, and then I need to make a new decision, I start from the top, and I don't really consider where I was before, what I was doing. It doesn't have any memory. It just, it's reflexive. It just does things. It doesn't consider what was going on in the previous step. Does that make sense? Nice. Can you come up with a decision tree? Do you want a moment to see if you can write one down? Just as a small exercise. Let's just do a couple of minutes, because I think it's not that different than when we were doing the finite state machines. So let's say a couple of minutes, and let's see if you can come up with a nice one.
Potentially using a decision tree for
Ah,
using a bunch of timers and stuff.
yeah.
Player health as the factors.
Yeah, that's a good idea. Yeah. Yeah, exactly. So these are the actions at the end, and then we have some. That's a very good idea. I think this might work potentially better as a decision tree, because it's not really. I don't know how much memory. Well, okay, I know it keeps some memory. Probably is something in between. Something.
Well, let's just do that though. Like if you had a tackle.
So, well, now we're getting in something a little bit different, but there they actually calculate this kind of tension curve. So depending on this curve, they make decision about how, like they want the tension to increase, and then at some point let it go down. So I'm not completely sure, but you're right, it could be, we could definitely use this as a decision tree. So we could have these as the final leaves, and then make decisions based on, are the players all together? Yes, no. Are they, do they have a lot of health? Do they have small health, or so on? So yeah, definitely. I'm not gonna draw it, but I think we get the idea, right? So again, very, very simple to come up with these stuff, right? What about coding it? How would you code this? Like if you look at that, right? Yeah. Yeah, it's if statements. Again, they're just coming back at us. These actually, it's super much if statements. It's just if statement at the top that inside, in the main clause and in the else, we have other if statements and if statements and if statements and if statements. So super easy to code again. Maybe there is a better way to make it, but we won't really go we're not really going to that. But at the very core, if statements are all you need, and that's very simple. Right. So last thing of today, and then you're going to be free. It's behavior trees. So basically, we've seen finite state machines. We have memory. We have transitions between different kind of states, and those states determine what our MPC does. Then we have the decision trees, where we navigate the flowchart to decide which actions to make. But these do not have any memory. They don't know, what we were doing before. So behavior trees are basically putting these two things together into something a bit more complex. This is a technique that became famous from Halo 2. It's the first time that was used. Bless you. In this case, the basic building block becomes more of a task rather than a state or these questions that we have in the decision tree. So how does it look like? Again, it's a tree, as the name says. So it has this type of flowchart structure. And we have a couple of different types of nodes inside. We have the leaves, the ones at the end that are usually conditions, actions, some sub-behaviors, something like that. Then we have internal nodes, which are either composites, which we're going to see in a moment what they do, and decorators. And the cool thing here, the real innovation in this one, is that the nodes have states of themselves. So they're not just nodes, internal nodes, like in the decision tree, where we just ask questions and we don't care about anything else. These actually keep some kind of memory of what succeeded, what failed, where are we right now while we explore this tree. And this really is the trick. We'll see how it works. For about how they work, just as in the decision tree, we start from the root. We always start from the top, and then we explore the tree using the rules that the tree defines. The other interesting thing is that instead of making the decision in one frame, we just go through the tree, we decide what to do like in the decision tree. Here we can have nodes that take multiple frames, multiple ticks, so we can just maybe have something that's long. We just start doing it, and we wait until that finishes before we continue and do the next part of the behavior. So building blocks, composites, nodes that have more than one child. In theory, they could also have one, but most of the time they have more than one because it doesn't make that much sense. So they could be sequences of actions, things that we want to do in some specific sequence. Selectors, maybe things that decide, I want to do one action, but there could be one of many. And in some implementation, there's more than this, but these two are kind of like the core ones, the ones that are inside any implementation of behavior trees. For decorators, it's nodes that have only one child, and basically they are modifiers, really. They change what the output of the child is. Let's take a look. A sequence could be something like this. So it's a composite node, so something that has more than one child. And the idea is that we want to do this one after the other. And if I, for example here, if I walk to the door and this succeeds, then I want to open the door, right? And so on. Afterwards, I want to walk through the door, close the door behind me. So we can create these actions that are more spread out and more, like complex or built of different smaller tasks. What do you think happens if I can't complete the sequence? Yeah, so if we can't complete one of these, we basically stop, right? If you think about this from a point of view of logic, if I walk to the door and I try to open the door and it doesn't open, there's no reason for me to try to walk through the door, right? Because the door is not open, I just can't do it. So when one of these fails, we just stop there. We don't continue trying to do the other ones. So if one of them fails, the entire sequence also fails, because it means that this sequence of going through a door didn't succeed. Another example could be something like this. So, am I hungry? Yes. Then I move to, do I have food? Yes. If that's a yes, then I can check if there are no enemies around. And if that's also true, then I finally eat the food. If any of these things fail, then I can't get to the end. I can't actually eat the food. For decorators, this is an example. It's a pretty typical one called an inverter, which basically just flips the result. But in general, they add some complexity to a single behavior. For example, in this one, it's the same as the one that I had before, but instead of having that no enemies around, now I have enemies around, and the inverter just flips that. So if there's an enemy around, then this becomes kind of like flips it around, so it becomes false, and I can continue and so on. There are a few different ones for these. For example, there's a repeater, something where you can run the child more than once. So imagine that we maybe this is shoot the player. We want to do that X amount of times before we move on to the next step. So it could be like, instead of having 10 nodes that say shoot the player, 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 we just have a decorator that says repeat this 10 times. Filters, something where we can check, for example, how many times this behavior runs. Maybe we don't want to do this for too long. Maybe we're going to try to do something, but if after 5 seconds that hasn't succeeded, maybe we should move on to something else. Like adding that kind of timers and stuff like that is what filters can do. Managers, where you can handle different information. It doesn't matter. We'll just move on. It's a bit less. It's a bit more of a smaller case. And you can also have stuff that helps you during development, so like debug stuff, adding breakpoints, logging, some stuff. So usually most implementation have a few of these and a few of the ones that are more useful for development, and then you would take them out once you're done. Finally, the last one I want to show you is the selector. It's a bit like a sequence, so it's still one of those internal nodes that have more than one child. And in this case, for example, a priority selector means that we want to do one of these 3 things, but only one. So for the priority one, they are ordered. So we would try to do the first one, and if that fails, we would try to do the second one, and if that fails, we would try to do the third one. So you see, in this case, we have the same thing of walking through the door from before. If I got to the door, then I can try to open it. If it works, great, done. Let's move on to walking through. If it doesn't work, I can try to unlock it. If that works again, great, let's move on. But if I can't unlock it as well, I'll try to smash it. And then we can move through the door. So basically, do the state 1. If it succeeds, you're fine. Otherwise, you try the next one, and you try the next one. And if all of them fails, then the selector has failed. You can't really do anything else at that point. There's also some other ones where you can do things based on probability or randomness. So same idea, that you want to have just do one of those, but instead of doing this priority thing where you try one and then try another, you just pick one at random or with some kind of chance, and then you use that one. Exactly, like small variations for animation, or maybe if your NPC is kind of done with everything it has to do, then maybe we're gonna go on patrol, maybe we're gonna, cook some food, maybe we're gonna do something else, so you can create more variation of what the NPCs can do, instead of having like a set pattern, like it would be in a finite state machine, for example. All right, so last thing I want to show you is the thing about the states. So let's try to run through what happens when we run a behavior tree. So as I mentioned before, we have these states for each one of the nodes. When we start, they're all set as ready. That's kind of like the basic state of the tree. And then when we start visiting, we start from the top again. We change the state to visiting, so we can keep track of what are we doing within the tree at this point. So what do you think happens now? What do we do? Yeah, so we go to walk the door, right? We set that to visiting because now that's where we are. The sequence at the top stays visiting because we aren't done with it. Like, we're still in the process of doing it. And maybe that takes some time, right? Because maybe the door is very far. So I don't want to just say, I stop here, I fail because I'm not at the door. Maybe I'm gonna take some time and see if I can reach the door or not. So walking might take some time. We change state to running. And then maybe we wait, a second, a couple of frames, I don't know, some amount of time between when the first time we started the tree and when we check again. So after a while, we check again. Do we start from the top? Probably not, right? We start from the running node. Or if we want to reconstruct this, we just kind of like follow the visiting nodes until we find the running one, the one where we are at right now. But we could also just keep a reference to the running one. So we go back to this. Have we reached the door? Let's say yes, right? Now we change the state again because that's finally finished. It becomes success. So now we can move on. Where do we go next? Yeah. Now we move on to the selector because in the sequence, now this part finished and we can move on to the next one. So let's say that we check the door, we try to open it, but we can't, it's closed. So we failed that step. So what do you think happens now? Oh, yes. So it would be visiting, then we visit this. Let's say that this is an instantaneous action, right? Because it's just like, either it's open or closed. So if it was something that ran longer, we could have changed it to running again. But since it's probably a very instant thing, it just goes either to success or fail. So let's say it failed. What happens now? We move to the sequence, right? Because the selector wants to have one of these succeed, just one of them. But since this failed, we move on to the next one. Perfect, so that becomes visiting again. And now we try to go down to unlock the door, right? I skipped a couple of steps here just to make it a little bit quicker. But let's say that we managed to unlock the door and we managed to open the door, so everything else was a success down here. What do you think happens now?
Go back up. Sequence, success, success, and go back up.
Exactly. Since this sequence has succeeded, all of the child nodes have gotten a success. This also becomes a success. The selector just wants one child to succeed. So this also means that the selector succeeds as well. And we can move on to the next step of the sequence when we walk through the door and so on. let's assume everything works fine, so we get everything that succeeds, and the entire sequence, the root of the tree also has gotten to a success. Perfect. What happens now? We're kind of done with the execution, right? We went through all of the things that we could do until the whole tree ended, either in a success in this case, but it could also, of course, be in a failure. If we want to run it again, now we just reset everything. All the states go back to ready, and we can start again, all over. And I mean, there's no, of course, guarantee it will work the same way, right? Maybe the next door, we won't have the key, so we can't open it, so we'll try to smash it. Maybe we can do that, maybe we can't. So just to complete, before I just give you a couple of last remarks, does it make sense? Any questions? Right. All right, perfect. Then just the final remarks, and then I think we're a little early, but I think we can stop here because it's been a long day, I think, for everybody. Sorry. Why behavior trees? Again, nicely humanly editable. Again, you can ask your designer, come up with this. You know, you tell them the structure, you tell them they have these building blocks, they can build it. They can write it for you, and then you can try to implement it. So that's also very good. Designers love that stuff. It allows for a bit more complexity because you can keep memory, you can have behaviors that last longer instead of being instantaneous like in decision trees. So it takes the best of both worlds. You just really put together the two best things about the other techniques. And the other cool things is that this can also be learned. It might be a bit more difficult than learning decision trees, but there are ways that you can create this. You should ask Joey because we're both a lot into artificial evolution, and that's one of the techniques that's been used to evolve these things, to create them from scratch. Right. How do we use them in Unity? That's the last thing, and then I'll let you go. As you can imagine, these are a bit more complex to implement than the other techniques we've seen. And this is probably why, while they're popular, they're not everywhere. That's the main problem, I think. It's a bit more difficult, and there are some implementation on the Unity store. I'm assuming some of them are good. I just don't know, because a lot of them cost a lot of money, actually. I mean, a lot, you know, like we're talking like, I've seen some around $80 or something like that. So it's not impossible. It's not a crazy amount of money, but it is money. So I don't know about those, but I'm sure there's some there that are good. There are a couple on the Unity store that are free. I took a look at this one, which looked nice. The only thing is that it didn't have a visual editor for the trees. The trees are built through code. It looked all right. I think that was quite nice, but not super accessible. I think especially for new programmers, it used a lot of shorthands and things that might not be super easy to understand. So, the other one that I found is this one called Behavior Breaks. I used it at some point for some classes. It's all right. It has a graphical editor. But it's not very well documented, and I checked, it hasn't been updated since, I don't know, 2019, something like that. So it's getting a bit dated. I tried to import it into 2023, and I think it still works, but you get a few warnings that they're using some deprecated functions, so it might not work in some time. For now, it's still working. But you can take a look at that. It has a nice graphical editor, so you can actually put together the tree graphically. And of course, you can code your own. But I have to warn you that I had a student do it for a project, and it took him a lot of time. So it's not super easy to build your own. But it might be the easiest way in the end, because again, I think that this one, from what I remember, didn't have a very good documentation. This one looks better, but maybe not super accessible. But yeah, I think that's it for today. Sadly, I don't have an exercise for you with behavior trees, but I would suggest you take a look at those packages and play with it, see if they work or if they work for you. That's it. Thank you very much. That's it for today. Thank you.
Are we live? Yeah. All right. Hey, everyone. So we're doing the Blender workshop. Thanks for coming out, for everyone who's still here. I'll put back up this link in a sec, but first we're just going to talk about what Blender is and why you should use it. First of all, it's free. Open source software that's super powerful. You can do everything from 3D modeling, animation, or physics, sculpting, like anything you want to do if you're a 3D artist. Blender can probably do it. So that makes it a great program for learning how to do anything 3D related. And there's a ton of resources online, which makes it one of the easiest programs to learn in terms of just the sheer quality of the resources that's available online for free. So a little bit about me. I'm Dredge Stenner. I've worked as a freelance artist for Blender. I did it for like a year, and I've been doing Blender for a while. And yeah, so to download the course materials, you can just go to this link. It will be a Google Drive folder with a zip in it, and that will have a portable Blender install and some of the course materials that we'll need for this course. So I'll just give you guys like a couple minutes to do that and just extract it to your desktop or whatever. Here, so done here. It's slow? That sucks. That sucks for you. Let's see if it's slow. tinyurl.com/blenderworkshop. Yeah, for some reason on the version, I don't know why, but extracting stuff on these computers is really slow. So if you go to 7-zip, it should be installed on it, and then just find the file, and that will extract it like 5 times as fast. You just need to figure out where it is on your hard drive. Downloads. Blender Workshop. I don't know what Reese is talking about. Mine downloaded pretty fast. All right. Everyone good for downloading Blender? Or are we still waiting? 39%, wow. That is actually impressively slow. Yeah, so just open 7-zip and just go like users. I think it will be your student number, and then downloads, and just click extract. Extract right there. Oh wait, no, you need to.
Hold on, let me make sure it's the right one.
Wait, yeah, sorry. Yeah, double click it. Yeah. All right. What's it doing? It's okay. So go to 7-zip. This is.
But more halfway.
No, it's not gonna work. Like the Windows one is just broken on this for some reason. So go to users, default, downloads. Now Right-click and 7-zip, extract here. There you go. All right. All right, we good for, all right, we got Blender open. Are you good?
Yeah, I'm just extracting the folder.
Yeah, I don't know why, but like that one just, I think you need to use like 7-zip or something, because the default Windows one just doesn't extract it for some reason.
That's weird.
I know, it's super weird. All right.
It extracted, but you have to do more to launch it? Or is it because I already downloaded it?
Because the side-by-side config is incorrect. Blender, oh, because it didn't extract all of it. Just, let's delete that. This is the one we want.
Well, I already have it downloaded from when I did it, but
Oh,
what else do you have in that folder?
so you've already extracted it. It's just this course materials folder.
Oh, okay.
All right, Josiah, you can just use my one here. So this will already have everything like on it. So there you go.
What are we doing?
So, course materials. All right, this is the Blender workshop. All right, you're good?
Yeah.
Kenji, are you good?
I'm downloading it.
All right, can we start?
I like this filter. It's like grunge texture.
All right, so but it's here. I'll just write it. Do you want me to write it down for you?
What thing?
Where to download the stuff.
Oh, sure.
So tinyurl.com/
So originally it was only for using it for Fall Guys
game.
because my other account, the one that I had, Fall Guys.
url.com/
So like it was
TRUSU
with
game
another account, like
dev.
because in Xbox you can only play with the same Epic Games account, and I can log out from there.
Go. So just extract that onto your desktop or whatever once you're done. You might need to use a different program like 7-zip to extract it. No, it has Blender with it in like a little portable.
7-zip.
But honestly, I might install Blender like that. I'm not sure. Like, here, just try opening it once it's done. And if you can't extract it, then try 7-zip. Is it? No. All right. I think I'll just start because they can figure it out. I don't know where Josiah went, but Kenji, you could probably just use the computer over to the right. It has Blender already on it. So, all right. So, I'm guessing most of you guys have Blender open now. So if you don't, just go into the folder and then just open Blender right here. And all right, so the basics are, so over on the left, we have a little toolbar. So this is the move tool. You can use it to move around the cube. So just try messing around with it. And then on the right, and then right below it, we have the rotate tool, which can be used to you guessed it, rotate it. And if you click on the side over here, it will rotate basically relative to your view, which can sometimes be a little confusing, but other times very useful. And then right below it, we also have the scale tool, which can be used to scale things. So if you wanted to, say, make the cube a bit taller, that's the tool you'd want to use. All right, so does everyone get that? All good? All right. So now we will commence in one of the most important things in Blender, which is deleting the default cube. All right, so to do this, we hit X, and then we'll get this little prompt. It says delete, and now we hit enter. Goodbye. So now we do the second most important thing in Blender, which is adding back in another cube. So we go up here, add, mesh, and cube. And then if we want, we can just keep doing this over and over again until we have some ideas. All right. So if you go up here, you'll notice cube isn't the only option, which many people don't know this, but there's a couple other options here. So the one that we'll be using is the UV sphere. So this is our first little project. We'll be making a snowman. So let's go up and click Add, Mesh, and UV sphere. Right. So now that we have a UV sphere, what we can do is just move it around. Let's just move it up like just above this line. And what we could do is we could add in another sphere, but since we're lazy, we're not going to do that. Instead, what we'll do is hit Shift D. You can see what I'm clicking, what buttons I'm pressing down here, and duplicate it. And let's just move it up a bit. But you'll notice it kind of moves around. So if we want it to only go up, we can hit Z, and then we'll move up on the Z axis. Which, yes, Z up, not Y up. Get owned, idiots. All right. So we can use the scale tool and scale it down. Just like that. And let's duplicate it again. And Z. And there's also shortcuts. So if we hover over this, it will say what the shortcut is. So instead of going over and hitting the scale tool, what we can do instead is just hit S, which is what I'll usually be doing. However, if you like using the tools on the side, feel free to use those as well. And then I'll use G for grab to move it down. All right, we're good?
Doesn't look right.
Fuck. All right, so now that we have this, we'll probably want to give him some eyes. So we can, once again, just duplicate, give him some eyes. So move, duplicate, and just that sort of thing. All right. So if you have this now, what you can do, so what you'll notice when we add in an object, it doesn't quite, it sometimes won't appear where we'd expect it to. And that's because it spawns your objects at the 3D cursor, which is this little thing over here. If we hit Shift and right click, we can move the 3D cursor to a new place. So when we add in, say, a cone, it will go where his nose is. And then from there, we will just have to rotate it and scale it down and move it out a bit. Yeah. So now we'll also want to probably give him some arms. So what we can do is add in a cylinder, and let's go to the scale tool and just scale it up first a bit, and then just scale it down. So we have a nice little stick. What? Shifty. To move the 3D cursor, hit Shift and right click.
I didn't do anything.
What the fuck did you? What did you do?
What do you mean?
What did you do?
What do you mean? It looks good, doesn't it?
What is this?
It looks good. My snowman. Fuck. Thank you.
All right, man.
I need another head.
All right. This making sense. Oh, I would plug in a mouse. I can get you one for you.
Sure.
All right. Go. So if you yeah, it's use the middle mouse. You can click it down and then rotate. And if you hold Shift, you can pan. All right. Let's start a new file, Reese.
No, I like it. Jory, my snowman. It looks so good.
Here you go. All right.
No, he's ugly now.
I literally can't.
Can you bring back my old guy?
Oh my gosh.
No, I don't.
Fine, I will. Here.
Go back to my old one.
Here, autosave. You suck.
Where'd it go? There it is. She's beautiful.
Stupid.
No, bring it back.
No, she's saved. You can open her anytime, Reese.
I don't want to look at it. I want to make my snowman like that.
That sucks for you. All right.
Okay, whatever.
Here.
The whole point is I'm meant to be doing it.
Well, you're like falling way behind.
No, it doesn't matter.
Okay,
how
so you-
far behind I am.
Yeah, it does. All right. Is anyone out? I hope you guys aren't as far behind as Reese, but
I'm not far behind. You just deleted my shit.
she literally had like a single object that was distorted. All right.
Well, she tried.
She did her best. All right. All right. Oh, right. You can also hit middle mouse to just pan around. But, oh wait, no, like when you click it. Yeah, okay, good. Sweet. All right. So. All right. All right. Do you think I should just go ahead,
Yes.
All right.
No reason.
All right. So so if you guys are up to here, if you guys don't have everything quite like this, that's okay. But so we're just gonna hit middle mouse and just pan over to the top of his head. And once we're looking over on top of it, we'll hold down Shift and then right click to put our 3D cursor on his head. All right. Now with the 3D cursor on his head, we will go to Add, Mesh, and go to Cylinder. And we'll just scale it down a bit like this. And we're gonna make a hat, but we don't want to add it, but this doesn't quite look like a hat. Even if we were to scale it up, it would be kind of a stretch to call that a hat. So what we can do is hit Tab to go into edit mode. And there will be 3 selection modes. So there will be vertex, edge, and face. We'll want to hit face and select the top face up here. So again, you can hit Tab or just go up here to edit mode, select face, select, and just select the top face. All right. Sweet. All right. So with that top face selected, what we'll do is hit extrude. We'll hit extrude region and just scale it up, move it up slightly. And then we can use the scale tool to scale it down. And this time, instead of using the tool over here, we can just hit E, which is the shortcut. And just like that, we have a little hat for him. And I'll just go over the steps for the hat one last time. So just go up to Add, Mesh, Cylinder, then we'll use the scale tool, or S and Z. And let's just hit S again to get it about what we want for the base of the hat to be. Go hit Tab or go up here to edit mode. Select face select, which we can hit with 3, and so select the top one. Then E for extrude, S for scale, and click to confirm, and hit E one last time, and then just click to confirm once we like the height. All right. I'll just go around and check up on everyone. Except Reese. All right, you good? Are you? All right. Yeah, so these also have some arrows if you want to just move it in one direction. Yeah. Yeah, so yeah, it might not be exactly where you expect it to, so make sure you pan around. Actually, I'm surprised. usually it ends up somewhere else, but yeah.
What you just did, like cone for the nose.
Yeah. So let's just skip ahead a little.
Sure.
And go up to add. So we can move the 3D cursor. Actually, here first let's pan to the top of his head and hit Shift and right click, and then click Add Cylinder, and just pan down, hit, and then use the scale tool. Yeah.
Something like that.
Yeah, and then you can hit Tab to go into edit mode and select, and now there's 3 selections: vertices, which are those points; edges, which are those edges; and the faces, which we'll want to use face select. And pan up a little so we can select the top face. Yeah, just click it. No, just click it once. Yeah, you got it. And then hit E to extrude it, and then S to scale it down. And yeah, just undo that real quick. Hit E and then extrude. Sorry, so S. Here, it's just, there you go.
Okay.
And then hit E again and move it up, and then you can confirm. Go.
Okay.
Yeah. So that's how you use edit mode. All right. How are things for you? Oh my God, Reese. All right. All right. All right, so now we are going to save our file. So if we go up to File, and then up on the top left, File, Save, and I'll just put mine in Documents. Let's name him Snowman. All right. Snowman. And once again, that's just go up to the top left, File, Save, and just name it whatever. And also, just as a quick request, just add Snowman and then just put like your name. Because, yeah. Afterwards, I'm hoping to 3D print some of these, so you can just send me, so you can just save it and then just send me it over email and you'll have it tomorrow. What? All right. Everyone good? All right. And just as a quick request, if you see someone else around you, like once you're done something, just make sure that your neighbors are all up to speed. And if they're not, just try to help them out. That'll help the workshop move along a bit smoother. All right. So now we're going to make a new file. So go up to File, New, and then go to General. And you know, this time, I was going to save this for a little later, but I think we're going to do a special way of deleting the cube. All right, so this is about the cube. All right, cubes. Every day, artists around the world kill their cube. This is sad. So you can see endangered species cube. He's sad. So what are we gonna do? We are going to kill it. We're gonna kill more cubes, but more creative ways. All right, so this first method is called free fall. All right, so this one's pretty simple. You just go up to your objects, go to rigid body, and add active. And then you just hit play, and let's see what happens. All right, object, rigid body, add active. All right. All right, now it's falling into the void. All right, so this is a little thing about the menus. So all menus in Blender can actually be resized or changed to whatever you want. So if we click on the bar here, we can increase the size of our playback. And just go over here to the corner of it and drag it to the left, and we'll get a second window. And if we want to get rid of that window, we can also just hit the corner again and just drag. All right, and now we will, with this second window, we'll change the playback to video sequencer. All right. And over here, we will have a couple tracks like you would see in a video editor. Now, all right, so once you get here, you can go to Add, Sound, and just go to the course materials and then go to Scream. All right, now let's see what happens. Let's turn up the volume to make sure it's good. All right. All right, there we go. All right, thank you. All right. All right, and since we already have the rigid body, we will do the second method, which is implosion. All right. So you just drag to the side, go to video editor, video sequencer. All right, so this is implosion. So one of the things that happens is if you have some rigid bodies intersecting with each other is that they'll go flying. So if we just duplicate the cube with Shift D, you'll notice it kind of goes flying. But if we do a lot of them, it gets more and more intense. So what we can do is instead of giving ourselves arthritis by repeatedly duplicating them, instead what we can do is hit Shift D once, and then hit Shift R to repeat our last action, and we can just hold that. So we'll just do that, and oh god, there we go, beautiful. All right, and this, assuming we get through the full course, this isn't for nothing. We will actually use some of these techniques later in the course. All right. Just change the pace. All right. Sorry? Oh, we'll get to the animation one later. Oh.
You know how you have the playback and then the video editor? Is there a way to get it back to default? Just everything?
Oh, you can, if you want to bring it back to default, you can just hit plus, general, and then layout.
Oh, I see.
And then you'll get the default layout. All right, so now that we've done that, we'll just make a new file. You can. You just hit S. If you want to make it smaller, you can just hit S, and then drag towards the object, and it'll get smaller. All right. So we will now be doing our second project, which will be our pencil. So in this part, we'll be learning about materials, as well as a bit more about edit mode. So if we go back to our Blender, we have the cube, and if we wanted, we could just do this again. Goodbye, and then just hit X, delete. So we'll go up to Add, and go to Cylinder. So once we add in a cylinder, there will be this little, don't click anything, but there will be something down here on the left, which says Add Cylinder. And if we open that menu up, it will give us some options. The one we're interested in is the amount of vertices. So if we turn that down, it will get more or less polygonal. And we want to we'll just click it and set it to 6. That's how much, maybe 8. Let's do 8. All right. So once we've done that, I'm just going to look around just to make sure everyone's all good. Oh, yeah.
I did not manage to follow the
So, okay, so just delete that, add back in a new one, and make sure go to the left, and then set the amount of vertices to 8. Oh wait, so we're on the pencil project.
Yeah, I'm trying to extrude a cylinder.
So what you want to do is add in a cylinder, and then click down there, and set it to 6. Under vertices. All right, we're good. Reese is not good. Okay, you're good?
Oh, yeah.
Sweet. All right. So let's just quickly move this up with G and then Z, and hit Tab to go into edit mode, which is what we used to make that hat earlier. We'll go into face select. You can also, by hitting 3 or going up here, and just selecting the top face, and let's just move it up a bit. Now it's a little bit taller, and we'll want to select the bottom face, and let's just hit E to extrude, and then left click just to confirm, and S to scale down. Now we got the little tip of a pencil. All right. And now once we've done that, what we can do is extrude this up, the top face, move it up, and we'll use a new tool, which is the loop cut tool. If you go over here, you can use the loop cut tool. And I like using loop cut. Usually I just hit Control R to use the loop cut tool. And if you use the scroll wheel while you're using, you can change the number of cuts. So, or you can also just manually enter it. So we'll set it to like 4 cuts, like this. And this will create some edges along the loop of a face. And once we have those, just Don't deselect anything, but we can hit Control B to bevel it. And now we will have some faces here. And we'll change our select mode to face. And then we'll hit Alt-E to extrude and select extrude faces along normals. And we'll just extrude it. Let's do it out a little, like this. And I'll just do that one time more from the start. Well, not the entire start, but yeah, let's just do it from the start. So we moved this up using the move tool. Selected the bottom, so we're in face select mode. Extruded it down, scaled using S. So E, S, and selected the top, E, to move it up, and used the loop cut tool with the number of cuts set to 4. Then we use the bevel tool to bevel it, which is, or the shortcut for that is Control B, and we hit Alt E to extrude along normals. Very good.
Why can't I scale smaller than this? Back.
Hit Alt E. Yeah, Alt E.
Look.
Do it along normals. Because you have the solidify modifier. Then disable it. All right. All right, how are we? Wait, what is going on here? Oh, change it to 8. Yeah. What is this? Here, let's use the add menu. All right, mesh, cylinder, all right. Here. Sweet. All right. So, okay. Oh, so here, what we can do instead is if we want to select, like, just, oh wait, what is this? What's happening? Oh, okay, so if we want, so a little thing we can do to select these is hold down Alt and Shift to just select a loop. And just do that for all of those, all 3. So, one, select that one, and that one. Oh. Yeah, so now hit Control B to bevel it. Yeah, like that. Yeah. You can just hit E and then hit S to move it out a bit. We can hit Shift Z just to make it do whatever looks right to you. All right, and the other thing is go select the bottom face. Bottom face. And so let's just pan up a little. So middle mouse, extrude with E, and then confirm what, and then get it however it looks right to you, and then S to scale it down. Yeah, confirm. Oh yeah, so yeah, that's good. What's probably happening is that you are scaling it while your mouse is too close to the selection. You'll want to move it out a little first, and then, yeah.
It's good. Fix it. Crashed for a second.
All right, moving on. All right, so let's go to the top of our pencil and select the top face and hit Shift D to duplicate that face, and we'll hit right mouse just to or we'll just hit Escape to move it back to its original position. So again, I'll select the top face, Shift D, and then hit Escape. Once we've duplicated that, we can hit P to separate the selection. And now we'll have a new object that's just the top of it. So we'll go back into object mode, and I'll just do that one more time. So you just hit P, selection while you have the duplicate of selected, and then selection, go back into object mode, and change our object to just the face on top. If you're having trouble selecting it, you can also use the object selection menu on the top right. Control D. E. Tab. All right. So we'll select the top of we'll select our new object, go into edit mode, and extrude this up. All right, and just select the new object, edit mode, and extrude up. Once we've done that, we can go down here to the bevel tool or hit Control B. And if we bevel it like this without doing anything, it looks a little blocky. So what we'll want to do instead is change the number of segments, or if you're using the Control B, and you can use the scroll wheel to change the number of segments, which will basically make the bevel a little bit smoother. Once we've done that, you'll notice the eraser still looks a little blocky compared to the rest of the pencil. So if we go to the blue wrench over here, to modifiers, and click Add Modifier, and do Subdivision Surface, which is down here, it will smooth it out. But there's a little bit of a problem, which is that it kind of goes inwards a bit. And to fix that, we'll go to edit mode and go to loop cut. And just add, and we'll just use Control R for this one with one loop cut. Control R, one loop cut, and move it. And once we click it, we will have the option to move the loop cut, and we'll move it down to the bottom. And that will just fix it. Yeah, we're good. Good enough. Okay, I'll show you afterwards. All right. Good job. All right. So hit Tab and hit Control R for loop cut. Click once, and then drag down. Yeah. Yeah, and then you can hit Tab again. All right.
They edited the pencil instead of the.
Oh yeah, that's good. I feel like I might have made mine a little too smooth. Whatever. Okay. Oh, here. So let's just hit undo a few times. What's this? Okay, so we just need to, before we do anything, we just need to separate the object. So I'll just select just that bit, and then you can hit P, separate, and then do selection. Then go back into object mode and select the top and go back into edit mode and select the top face and increase the amount of segments for your bevel tool. Do like 4. And then do it whatever looks right to you. You don't have to copy my example. That's fine. Okay. All right, and then go back into object mode. And to smooth it out, you can go to the blue wrench, which is the modifiers tab, and add in a subdivision, add modifier and subdivision surface, which is right there. And let's just scroll up a little.
What do you mean scroll up?
Sorry, not scroll, I mean like move up. Yeah. Yeah. And
That might need to be brought out a little more.
yeah, but yeah, we can just go to object mode and then select all with A and just scale it out a little. Yes. Yeah, that's good. Just do whatever. All right. Sweet. So everyone's up to speed? I will take that as a yes. Yes? All right. Now we'll want to add a little bit of color to the pencil because it doesn't quite look like a pencil yet because I don't see that many gray pencils around, but so if we go down to the Material tab, so we'll go down to the right side of, and just select this little sphere. This is the Material tab. So I'll go down here and hit New Material, and change the base color. And you'll notice it's not really changing much. And that's because we are not in the rendered view. We will want to go from viewport shading to either material preview or rendered. So one of these two right here. And now when we change it, it should do that. And I'll just do that one more time. Hit New. So you go down here to the Material tab, New, and change your base color to whatever color you want. I'm gonna do a kind of pink eraser color. And then go up here, and then you can just hit Z and click Material Preview, and then just release Z. You just have to hold down Z, or you can just go up here to the menu. Okay. And we'll do the same thing to the pencil. We'll make this a yellow color. So Material menu, New Material, and just change the base color. And yeah, now unfortunately it's affecting the whole pencil, which isn't quite what we wanted. So we will fix that in just a moment. I'm just gonna go around to check on everyone, just to make sure it's doing good. Upright? Right here. Yeah, I would do the one Material Preview. It's to the left of it. Yeah. All right, materials, New Material, change the base color. And then you'll notice nothing's happening, so you'll want to go up there. Yeah, you got it. It's beautiful. All right, all good? All right. So now that we know how to make some materials, we will want to apply different materials to the rest of the object. So if you go over to if we select our pencil, and then we go to the material slot, and just click Add a new material slot, this will add in another material to it. And if we hit New, we can make this maybe a more brown color. So we can make it red and then just make it a bit darker. So again, just add a material slot, New, and change the base color to like brown. However, it's not actually applying anywhere. So to apply it to certain parts of the object, we'll want to go into edit mode. So just hit Tab, and just select this. But if we just tried dragging that part, you'll notice it doesn't do the whole thing. So what we'll want to do is go into wireframe view, which you can access up here, or by hitting Z and dragging to the left. And then you can select the whole thing in just one click. And with the bottom of our pencil selected, we can hit assign. And now our pencil will be brown. Maybe this is a little too brown. So let's do something a little lighter. All right. And we can do the same thing. We'll just add in another material slot. And let's make it metallic. So if we add a new one, scroll down, and there's an option called metallic. And if we do the same thing that we did with the bottom, which is edit mode, wireframe, and in face select, go into face select mode, and just select the top. And with the top selected, we can hit assign, and we will get a metallic material here. We can also turn down the roughness to make it a bit shinier, but that's all up to you. So scroll down, metallic, yeah, and then set it to 1. Okay. Yeah, like after it's done, I can do it. The next part, you won't need to do too much modeling, if any. So go into wireframe.
I'm just trying to loop select this, but
Don't, just trust me. Go to wireframe and then just drag box select the whole thing. Yeah. Yeah. Sweet. And once we've done that, we'll just add on the final tip, which we can get by going to edit mode, selecting the bottom, scaling it out, extruding it out with E, and then scaling it down. And we can go into wireframe and just apply it the same way we did with the other ones. So same thing, just go into add new material slot, new material, and make it a dark one. I'll just do that one more time. So select the object, edit mode, face select the bottom, extrude down, and scale. We go into wireframe now, and we'll make a new material that's dark, and just assign that. And there we go. Now our pencil is complete. I'm not helping you, Reese. No. Oh no. Oh geez. All right. You good?
Looking for work if I'm black.
Oh, so if we go on the side. Yeah, there we go.
Okay.
And then
And then what's
sign. And yeah. yeah, you'll, yeah. That was selected. Clicked off it. Yeah. That's okay. All right. Sweet. All right, so I think it's about time we'll move on to the next project. So we'll save our file, and for me, it will be pencil Jordy. All right, so file, save, and yeah, there you go. So let's make a new file. And just to change things up, this time we're going to set the cube on fire, all right? So this will be method 6, arson. All right. So we will go into our cube and go to Object, Quick Effects, and we will do Quick Smoke. And you'll notice it's smoking, but it's not on fire. So we need to select the cube, go into our physics, which is over here, which is this little blue thing, and select the flow type and change it from smoke to fire and smoke. And now if we go back to frame 0 and just hit play, now it's on fire. All right. I'll just do that one more time. So Object, Quick Effects, Quick Smoke, select the cube, go to this blue thing here, and change it to fire and smoke. And there we go. We have set it on fire. And now we can just delete it using X. All right. So now this part will be a little bit about shading. Here it is. So in the real world, there are almost no perfectly smooth surfaces. Almost all materials have some amount of scratches or some amount of roughness to them. It's the only place where you'll see something that's truly perfectly smooth will usually be in super highly controlled environments like the places where they make CPUs, like in fabs. So basically all materials in the world will have some amount of imperfections on them. However, by default in Blender, when we make our materials, they will actually be perfectly smooth, which, if we look at it, just doesn't quite look right. Like, if you were to look at this sphere and I were to ask you, is this real or is this fake? Like if I were to make a whole bunch of them, it's pretty obvious these aren't real. However, if we were to add a bunch of surface imperfections, it will look a lot more realistic. And that's what we will be doing in this project. So we will delete the cube, and this time we're going to want to go up to this shading tab. And we'll add in a UV sphere. And what we'll do is also right-click and shade smooth on the sphere. And now it will have a perfectly smooth surface. So again, we'll go over to the shading tab, right-click, shade smooth. And now we can hit new to add a new material. Now, this is the node graph. This is where you can make much more complicated materials. And it's basically what we had over here, except it has like all the same options, except now we can connect a lot more complicated things to it. So what we'll want to add is go to Add or hit Shift-A and search. We'll want to search for an image texture. Another way of doing this would just be select the base color, drag out, and then search for an image texture. Now, once we have this, we want to make sure it's connected, the color is connected to base color, and open an image. All right. Now, go over to the course materials folder, and there should be a file called 8-ball. If you aren't sure what the files are, you can go over here and go to display mode for thumbnails. So again, just click the add image and go to our course materials folder and open 8-ball. Might look like this, but if you want thumbnails, you can just do that. Click up here. Once we have that, if we connect it to our base color, we will get an 8-ball texture. Okay. So, like I mentioned earlier, this is just a little too perfect. It just doesn't quite look like an 8-ball. Even if we were to reduce the roughness, it just looks a little fake. So what we want to do is vary the roughness around it. So to do that, we can add in another image texture. So Shift-A, search image texture. And we'll click open. And if you don't want to go all the way to the course materials folder again, you can just hit recent, go to recent course materials. And for the first one, we will use grunge texture, the grunge texture. So we'll connect it to roughness, and this will add a little bit of imperfections, but before we can actually get the full detail out of it, for black and white images, we want to select our color space to non-color. And that will make this already makes our material look a lot more real. However, we'll need to make some adjustments to make it look a little better, which we will do in a sec. I'll just do that one more time. Image texture, open, course materials, and grunge texture. Then just connect it to your roughness socket. All right. So I'm just going to go a little bit more in detail about surfaces. Usually, there's also not just one type of surface imperfection. Like, if you were to have on this 8-ball, there isn't just, it's not just scratches. It's scratches as well as fingerprints and a little bit of imperfections from the plastic, but those ones aren't major, so we're just going to focus on the fingerprints and the scratches. But usually you won't find an image that's both of them. You'll only find fingerprints or scratches. So what we can do is we can combine the two textures. So if we go to Add, Search, then go to Image Texture, and search, go to our fingerprints, we can add in a new node, which is the Mix Color, and connect the two. And select the mix type to be Add. I'll just go around. And oh, and sorry, I forgot one last thing. Make sure the make sure the fingerprints are non-color as well. Okay. Oh.
I want an 8 cube instead of an 8
All
ball.
right. So go to Tab, U for unwrapping, and then cube projection.
Oh. That's close.
Yeah. Okay, this is like actually a bit more like annoying to do. Like I don't feel like explaining it. So I'll do it for you. Here you go.
Thanks. I just want the 8 cube because it's funny.
Sweet. Wait.
That's good enough.
Let's make it a little bigger.
Oh, perfect.
Sweet.
Cool. That looks really easy.
All right. Here. So select the base color. So see the little socket.
Yes.
And then click and drag out. And search for an image texture.
Oh.
Yeah.
Oh.
All right. Making good progress.
Yeah.
I can't believe you used light theme. 2 of them. Unreal. Nice. I love it. Did you have the course files or not?
No.
Okay, that's cool. So you have the 8-ball, connect the color to the base color. All right. I'll start from the scratch, just one last time. All right, so it seems like a couple people are a little bit behind, so I'm just gonna do this one more time. So we're over here, and you'll just want to go to Add and search for an image texture. All right, so Add image texture. And the option we'll want to select is to select an image for our image texture, we want to hit Open. And just go into our course materials folder and select the 8-ball texture. Now, to make this actually display on the material, we need to select the color and connect it to base color. And now we have our own little 8-ball. So I'll just do that again. Add, search, image texture, open, go to our course materials folder and 8-ball. Then just connect that to base color, like so. And we'll do that one more time, but this time, instead of connecting, so again, like add image, texture, open, and this time, instead of using the 8-ball, we will use the grunge texture. So open, grunge texture, and connect it to roughness. Select grunge texture. And make sure you set your color space to non-color, just for the grunge texture. That will make the colors just pop a little more, or not the colors, the roughness. And you can also duplicate a node like how you would duplicate an object. You can hit Shift-D, duplicate, and we will also have an image which is our fingerprints texture. And add in a node which will be the mix color node, and combine the two right there. And we'll want to connect that to our roughness. Connect the color to A and B. You can also zoom in a little.
Yeah.
So just move down more. So when you're dragging a node, if you just drag, it can automatically scroll for you.
Oh, okay.
And connect that one to A, and connect that one to B. We'll just also organize this a little.
Yeah. How are you going to move?
Yeah, so you just click the top of it,
Oh, okay. Nice.
or you can use G, same key used to move
Okay.
objects. And then we want to connect that to roughness, and make sure that your color space on these is non-color.
Why?
So it's a little technical, but basically in sRGB, a 0.5, sRGB basically uses a curve to simulate what a human would see. So a 0.5 brightness might be like 0.7, like in terms of how much it lights up your screen. But with non-color, if it's like 0.5, then it's 0.5. It's a little. It's hard to explain exactly, but
It's all good.
yeah. And you want to, instead of mix, you want add, which will basically just add the two of them together. And here we can shift and middle mouse. There you go.
It definitely looks more
Yeah.
weird.
And you can change the factor just to I. All right. And then final little bit, it's just instead of mix, we want to use add. And we can just play with the factor until it looks about right. However, even this is a little too rough. Like if we go back to our example, it's a little bit roughed up, but not like this. So to fix this, the node we'll want to use is called a color ramp. So add and search for a color ramp. And so the color ramp and we'll want to connect our result into the color ramp for the add. and connect the color amp's color into roughness. So again, add color ramp. And as we move these handles, you'll notice it kind of changes the appearance of it a bit. If we want to have a better idea of what's actually going on with the color ramp, we can connect the color straight into material output over here into the surface. And basically what this does is it kind of compresses the range of your material, or it basically lets you just take, like, if it was half bright, like a 0.5, then it will basically like put it on this scale, on this little like ramp. I don't know what to call it, and then can like kind of change the color using this, like. So if you wanted it to be higher contrast, like that would basically make some spots super rough and some that are super smooth. So you can just play around with that. But one of the more important features of color ramp is that you can also change the color, or in this case, it would be the value. So if we wanted the overall image to be less bright, we select the right handle, select color, and just turn down the value a bit. And we can do that, let's say like 0.5, and do the same with the left one. We can set that to like 0.1, let's say. So 0.1, then right handle, 0.6. And maybe even like, you can also just play with it, and just get it, whatever looks right to you.
Yeah,
All right. You know, here you can also learn about the color ramp. So if we were to bring that, actually here, we'll just do it on your base color. Now you too can with the color, so like, and if you add a new one, you can also like, yeah, or make the blacks a little, wait. Okay, make it, yeah. Yeah, you can just do it whatever looks best to you. All right. And all right, so let's try and make this look a little bit more like we're actually playing pool. So we can go to Add, Mesh, and Plane. And then just hit G, Z, -1, and that will put it directly below the sphere. And we can just scale it. Let's say, so I'll just do this one more time. So Add, Mesh, Plane, G, and then just move it down, but by -1. All right. Mesh, Plane, GZ, -1. All right. And then we can use scale and just scale out on the x-axis by hitting S, X, and then S and Y to move it out on the y-axis a bit. And let's just make something like that. And another cool trick is when you're moving, scaling, or rotating things, you can also click down the middle mouse and move to select an axis. So if we aren't sure, if we know the direction we want to go, but not what the letter would be, we can just like hit G, and then middle mouse, hold it down, and then it will show them, and just move it along, and then release, and it will let us select one of them. All right. So for this, we will want to create a new material, which will be and we'll just make it green. I'm just gonna mess around for a sec. Bump. Just need to make sure this works. Yeah, it works. All right. All right. So with our plane added and it scaled out a bit, we can add in a new image. So go to Add, Search, Image, and open, and we will, let's just use the grunge texture again. And connect it and add another node, which will be our bump node, and connect our color to our height. Then we will take the normal of the bump and connect it into the normal socket of our shader. And it looks a little distorted. So what we'll want to do is go into edit mode and select the top face, hit U, and click cube projection. And then with that, we'll want to go into cube projection and just change the size a little. Maybe something like that. And it looks a little too rough, so we'll turn down the strength. There we go. And also, let's just darken it a bit. So again, search for an image texture, and we will add in our grunge texture. Add another one, which is the bump node. Connect the color to the height and normal to the normal on our principled shader. Decrease the strength a little, let's say 0.2. Then, once you have decreased the strength to 0.2, increase the roughness of the table. All right. And now we can add just something in the background, just like a little cube back there. And since this will be largely out of focus, we don't have to worry too much about the details. We can just add in some cubes, scale them out a bit, and let's make a texture. Let's just make a new material that's another brown. So again, just add mesh cube, move it over a little, and scale it out. So good. Oh, so G, S, Z, -1. There you go.
Okay.
Yeah.
So let's. So just shortcuts.
Oh, those were shortcuts, but if you wanted to use it without, you would select.
Just the move thing.
Yeah, you'd select move
Okay.
and the blue arrow, which is the Z axis.
Okay.
All right. So base color, just set it to green. Maybe like a darker green. Weird. Oh, sorry. So you increased the emission. You just want to lower that. That's basically like a glowing. If it that makes it glow.
Okay.
Yeah.
Just couple of
Yeah. Maybe
angles to the sides.
a little darker. Yeah. Yeah. Add some cubes. All right. And for the cubes, we'll also want to make sure it's kind of a darker brown material. And we can just put these around this little area. If you want a better view for moving them around, if you go up here, you can click and it will give you a top view. Alternatively, you can hit S7 on the number pad, and that will let you just get to the top view. This works with all the other directions too. So you can select like a front view, side view, top, and same thing with the number pad. It's 1 for front view, 3 for right view, 7 for top, and 9 for bottom. So we'll just go top view and move these around. And when you rotate, if you hit R, you can type in an amount, number, like 90. So we'll rotate it 90 degrees and just move these around. So we'll hit G and move it over. And we'll do it for this one too. Now these don't have too much detail, but that's okay because it will be mostly out of focus. So we'll also just let's mess around with this. Let's maybe make it a little shorter too. I don't know. Like that. And we could maybe make the ball smaller too. See. Yeah. So we'll hit S and then type 0.25, and then just move it down a bit. 2.5. 0.5. Let's do 0.5. There we go. And then we'll move it down until it's touching. And once it's down like that, we can use the rotate tool just to kind of move around the ball so it looks a little more natural. So again, just take these, move them down a little, take the ball, scale it down to like 0.5. And then just make it so it's touching.
As far as I got.
Oh, this is good enough. Here, you can just, this is another trick. If you go to add cube, you can instead just drag.
Oh yeah. It's like text mesh probe, or not, it's like the pro builder thing in Unity.
Yeah.
I was trying to do the texture with like color ramps and shit. Instead of the texture, you know what I mean?
Which?
Click on the green.
Green?
No, like the green material.
Oh.
I had plans.
Oh, you had Voronoi. Okay, yeah, so.
But I don't think I was doing that right.
I'm just gonna use a little add-on. It's called the Node Wrangler.
Oh yeah. I've heard the
Node Wrangler. And then if you press Control Shift and click on something, you can just view its raw output.
Oh, I see.
So with us, we'll want to do the Voronoi texture. And the reason why it's not working is because your scale
This is all sorts of fucked up.
Oh, wait, no. It's because you have RGB in the vector.
Yeah.
So it doesn't really. So.
Oh.
Yeah, but honestly, I think I'd use distance if I had to do it.
Yeah, this is what I was trying to do.
And not use, and just make it a little.
Yeah, because you can do like cool textures with the Voronoi shit.
Yeah. Also, one other thing. This is, if you go to modifiers, you can add in a bevel, which will just.
Oh yeah, and then you can just make it round like that too.
Yeah, because in the real world, there's not really like perfect 90
It would be
degrees.
flat like that, but it's also a cube.
Yeah. Yeah, maybe like you could also have one color ramp going into like the roughness. So it looks really like allergy-ish, I don't know. Do you? Okay. All right, so we just have a couple minutes left. So we're just gonna wrap it up, but to render our image, by basically just rendering our images. So we'll add in a new object, which will be the camera. And then we'll just wanna move it just behind the cube, behind the ball. So if we want to view the camera, we can hit 0 on our number pad, or hit oh wait, no, we already have a camera. Let's just delete our old camera here. Delete our old camera. Or if you don't have a number pad, you can hit the tilde key, which is above the tab key to the left of the number 1, and select view camera. And if you want to like position the camera a little bit easier, you can hit Shift and the tilde key, which is again to the left of number 1, and that will let you basically just move around like it's a first-person shooter. So I'll do that. Move it down a little, and then I'll rotate our little guy a bit. And we will want to, we have like 2 minutes left. 1 minute. I'm just gonna speed run this. So go to camera, select our camera up here, go to data for our camera properties, and enable depth of field. Then then right click over here and select depth of field distance pick, and just click on our little ball. And change our f-stops and turn it way down, like way down. All right. Now if we were to actually go into our render view, which is what it will actually look like when it's rendered, you'll notice it looks all right, but kind of flat. So to fix this, what we can do is go into world, color, click the little yellow thing, go to environment texture, open, and go to course materials and select studio small. And that will basically just add some studio lighting to our scene. So it will look a lot more, I guess, professional almost. And if we want to adjust how blurry it is, again, that's the f-stops. And yeah. So now to render, we can go to render image. And there, if we also want to make it look a little better, we can also go to the little TV render and change our render engine to cycles, which just makes things a lot more realistic, because it basically simulates how light works in the real world rather than the ways it works in things like video games. So yeah, go to render image, and just hit render image and just wait for it. And there we go. So thanks for coming, everybody. I had like some other things, but you can, I'm sure you guys can find some resources online. Blender has lots of great resources online. One that I would recommend is the donut tutorial. Yes. You gotta do it, Otherwise you will never become a real Blender user. It's sad but true. Everyone has to do it. And yeah, that's about it. Thanks, guys.